Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and maybe this will be the last video that I do for the school year here, as we review for Integrated Math 1. The final review, at least for my kiddos, and maybe for your kiddos as well, whoever you are out there. Hopefully this helps you. In the description section down below, you should be able to find a download of the PDF of the, I think, 16 or so pages that I have for you guys here of review. The first 4 pages are my own based off topics that I would have probably covered in the first semester. Systems of equations, word problems, graphing systems of equalities, and exponential functions. I take it back. Exponential functions were always a part of it, but they were not a part of our mixed review. If you look at this PDF right here with me, I have systems of equations, word problems, and a system of inequalities one behind me right here where we will graph. Some exponential function review here, and some modeling, growth and decay, etc., percentage changes. And then we get to just this review, which is just a potpourri of different mixed problems. These are not mine, and a lot of them I'm not even doing with my kiddos. When I say a lot of them with the parallel lines and things like that. I see a typo already back here. This is an extra 12 pages right here, just going through. Every one of them, you can see on top, review worksheet number 1, 2 pages of that. And then review worksheet number 2, 2 pages of that, etc. Review worksheet number 3. And it just keeps going like that. There's 6 of those. So, what are all the different topics covered? I just mentioned before. Systems of equations, word problems, graphing systems of inequalities, just a single one of those. Exponential functions, exponential growth and decay. And percentage change. Within here, you can see things involving quadrilaterals, parallelograms, rhombuses, squares, and rectangles. You can see vertical angles, linear pairs. You can see transformations, angle addition postulates behind me right there. Triangle comparisons, isosceles triangles, and triangle inequality theorem is used here. Equations of lines parallel and perpendicular to other things. Angle bisectors, triangle congruence is one of the big ones that we're going to be talking about here as well. Perimeter, distance formula and midpoint formula. We mentioned before I find it, Pythagorean theorem will be a part of this as well. There's distance formula things right there. There will be a couple of proofs. Construction, there are a couple of construction questions, I think. Segment addition postulate, I just mentioned Pythagorean theorem before. Angle addition postulate, more on quadrilaterals, more on transformations, and more parallel lines cut by a transversal. A couple other things on exponentials. I think it's more interpreting graphs, not actually exponential functions. Parallel lines here and there, triangles, triangle congruence, isosceles triangles, transformation problem. Remote exterior angle theorem. Nothing new. Polygon angle sum theorem. More things with triangles, adding to 180 degrees within there. And more on congruent triangles and isosceles and equilateral triangles. And yeah, I guess no actual proofs here. Mid-segment theorem. All right, and that is a bunch of stuff we're going to be doing. A bunch of questions. You can see all of that for which I'm going to do with you here in just a moment. So in the description section down below, you should see a timestamp for every problem corresponding, and if not yet, then very soon from now. And you can ask me questions in the comments as you have them. I have a calculator with me right here. I have software calculator with me right here in case I want to show you something or in case I want to do something fast. Both of those together. And I'm going to go ahead and get started, guys. So let's go ahead and start with systems of equations, word problems. Now, in these ones right here, what you want to do is you want to define your variables so you can easily come up with equations and understand what your answers mean. So I'm going to be doing that for each of these. Number 1, you ride an express bus from the center of town to your street. You have 2 payment options. Option A is to buy a monthly pass and pay $3 per ride. Option B is to simply pay $5 per ride. A monthly pass costs $50. After how many rides would each option cost the same amount? And what is that cost? Okay, the 2 questions that are here are the ones which you want to answer. They are the ones which you do not know the answer to. After how many rides? We don't know the question how many rides we're going to have within that month. And what is the cost, the total cost, overall cost for that many number of rides? So we're going to define 2 variables here. These ones, if you kind of paid attention to what you just heard here, they're 2 payment options, how much you would pay, the cost, based on the number of rides. This is a dependent independent variable scenario. This is something where you have a rate that applies to a cost. This is like a good y and x that you want. We want x to represent here the number of rides, the number of bus rides, because dependent on the number of bus rides, you will get an overall cost. I don't know why that didn't hit as a register. And let y equal the total cost based on those bus rides. That's in dollars right there. So we have two different equations that we're going to write based on this, and defining those equations defining those variables can really help you come up with the equations. There's going to be an option A equation here. The option A equation, A is not a variable, it's just one of your equations, will be y equals, the total cost equals, you buy a monthly pass. That means you pay $50 for the month, regardless whether you ride any rides, 0 rides, 100 rides, 4 rides, whatever it is. You're going to pay $50 for that month. And then you pay $3 per ride. Well, if you rode 10 times, that's $3 per ride times 10 rides. If you ride X times, that's 3 times X. Here's your equation, 3X plus 50 equals Y. Option B, on the other hand, right here, is an equation y equals, where there is no monthly pass, but you do pay $5 per ride right here. So here's our system of equations. That is the setup. Both of these here combine the same system. We want to find out for which value of x gives us the same y, for which same value of x gives us the same y. Is it 10 rides that gives us the same cost? Is it 20 rides that gives us the same cost? Is it 2 rides that gives us the same cost? If you look at just one ride, after one ride, option A would pay $53 because the monthly pass. Option B would just pay $5. Option B sounds pretty good right now. But after how many rides does it take before option B catches up? That's what we're going to find out. This is where you solve your system. So I don't want to over-explain the solution portion of this, but I want to use the substitution method. Y equals this, y equals that. You can take this expression like 5x and substitute it for y, say in this equation right here. So you're down to just one equation with one variable. We'll have an equation that now says 5x equals 3x plus 50. If I subtract 3x from both sides, I'll get 2x equals 50. If I divide both sides by 2, I get x equals 25. That means that it'll take 25 rides for us to pay the same amount. So we answered the first question after how many rides would each option cost the same amount, after 25 rides. So 25 rides. Now, what is that cost? Well, the cost is based on 25 rides. I may substitute 25 in for x here or x here, and I should get the same answer. Let's check that out. Y equals 3 times 25 plus 50. That's 75 plus 50, which is $125. $125. Let's see if the other one holds up. Y equals 5 times 25. I'm getting an incoming call. I got to decline. 5 times 25, which is 125 as well. So you can see you get the same answer regardless. That's the point, right? That's important. So as far as answering that question here, normally you would write this as a full sentence. I'm kind of just going through, but I'll say it out loud. After 25 rides, both options would cost $125 each. It would cost the same amount. And after that, if you do 26 rides, you'd actually pay less money for option A, just $128 versus option B's $130. Depends on how many times you ride the bus in a month, but there it is. Okay, number 2. The admission fee at a small fair of $150, $1.50, let's see, is $1.50 for children and $4 for adults. On a certain day, 2,200 people enter the fair and $5,050 is collected. After how many children entered the fair? How many adults? Excuse me, I can't read. I'm a math teacher, come on. So, this is not a rate kind of way. I mean, there are rates, right? $1.50 per children or adults, but it doesn't amount to, there's no total based on the rates for each person. What you have is totals for a number of people and total number of dollars. Excuse me, hold on. It's not a y equals mx plus b kind of thing. We have two, basically, they are standard form equations. We have two standard form equations. So one of them is based off the number of people who enter the fair. 2,200 people enter the fair, and we have $5,050 collected. Two different equations, a people's equation and a money's equation. Now, we need to know how many children entered, how many adults entered. Again, those are our unknowns. Those are the things we get to define or things for. I'm just going to use x and y each time for these. Let x equal the number of children who attended the fair. That's fine. Just number of, not the cost per or anything like that. And y equals number of adults. So in defining the variables, it can help you come up with your equations once more. I can have a number of people equation that somehow we accumulate 2,200 people at the fair. How so? When you combine the number of children with the number of adults. The number of children plus number of adults equals 2,200. Anytime you write an equation, you should be able to flat out state what that equation is representing. And I can for you because I defined my variables. And I'm telling you, the number of children plus the number of adults equals 2,200 people. Now, this next one here, we can write some terms that come up with money for how much children spend, or how much adults spend for the children, but how much it costs for children and how much it costs for adults here. Total, $5,050 is collected. You collect money from children attending and from adults attending. Let's start with adults because the number is a little cleaner. It's a 4. $4 per adult. If 10 adults attend, that's $40 collected. 4 times 10. If Y adults attend, that's $4 spent. 4 times Y is how much money is spent for adults, or how much money is collected from adults attending the fair. Now, $1.50 or 1.5 times X is how much money is collected from children attending the fair. When you add this amount of money collected from children attending the fair with this amount of money collected from adults attending the fair, that's how much money you collected from people attending the fair. So here's your system of equations right there. So we'll go ahead and solve this one. There are a lot of different ways you can go about I'm going to use the elimination method, but there are a lot of different ways you can choose to eliminate things. One of my preferred go-tos generally is to not have decimals if I can help it. Like you could multiply everything here by 10. Heck, you could multiply everything here by 2 if you wanted to. I could say times 2, and then you have 3x plus 8y equals 10,100, like that. So there's a good rewrite. It just helps things look better for some people. I know they prefer to maybe not use any decimals if they don't want to, especially if maybe they didn't have a calculator. But I could do something now like multiply this top equation by -3 as to create an additive inverse for my x's. -3 times x is -3x. You can see how that helps. Minus 3y equals -6,600. I'll try and do this without a calculator as long as I can here. So 3x minus 3x is 0. 8y minus 3y is 5y equals, I kind of want a calculator suddenly, 9,33500, like that. So you divide both sides by 5, you get y equals 700. What does y represent? The number of adults. 700 adults attended the fair. How many children attended the fair? Well, 2,200 people did total, so you can substitute again. X plus 700 equals 2,200. Subtract 700, x equals 1,500. So 1,500 children attended the fair. 1,500 children, 700 adults. And you can double check all the work. See if you multiply 1,500 by $1.50 per child, then see how much money that is. Multiply 700 by $4 per adult. See how much money is collected there. See if that's a total of $5,050. It should be. But there's that right there. All right, Mr. Robinson, that is me. Mr. Robinson invested in 2 companies with shareholdings, AMC and GameStop. Did he really? It's up to you to find out. He purchased 12,350 total shares, purchasing AMC stock at $8.50 per share. Oh, this must have been last year. And GameStop stock at $90 per share for a total of $133,500. How many shares did Mr. Robinson purchase for each company? Okay, so for this one, it's very much the same as the last one that you saw here. How many shares per company? I need to know number of AMC shares, number of GameStop shares. Let's let X equal number of AMC shares. And Y equal number of GameStop shares. This is very much like the last one. I'm going to put GME. That's their ticker symbol. Why would I know that? Who knows? Number of AMC and GME shares here. When you add the number of AMC shares with the number of GMC shares that Mr. Robinson purchased shares for, then that totals 12,350 total shares, not dollars. That is a number of shares equation. We're going to have a dollars equation here that totals to 133,500, and that's based on the money spent on AMC shares and the money spent on GameStop shares. You spend $8.50 a share, you multiply by X shares there, you get how much money spent on AMC shares. You spend $90 a share for GameStop and you buy Y GameStop shares. This is how much money you spend on GameStop shares right there. So there is the other equation right there. Money spent on AMC, money spent on GameStop, money spent total, number of AMC, number of GameStop, number total. Okay, this time let's try this just in keeping the decimal. I'm definitely going to have to use a calculator ultimately for that, but let's multiply this whole top equation, say, by negative 8.5. Negative 8.5 here, negative 8.5 here. So we'll get negative 8.5x minus 8.5y. Let's multiply that and use this calculator because you know what I'm going to do. Negative 8.5 times 12,350. And I'm getting negative 104,975. When you combine like terms here, these cancel down here. And you're left with, I believe that's 81.5 y here. 133,500 minus that. So 28525. Now I'm only going to buy integer numbers of shares, I believe, so hopefully these can divide by 81.5, and I got 350. Y equals 350. That's not just shares, but that is GameStop shares. So 350 GameStop shares in total were bought. How many AMC shares? Well, I bought 12,350. So x plus 350 equals 12,350. It looks like x will equal 12,000. 12,000 AMC shares were purchased. So one more time there, that was an elimination method version of a problem based on how those things were set up there. You really just got to kind of look at how the problem is described for you and what kinds of totals there are. Is it some sort of rates to total to a same amount of cost, or is it different situations like these right here? All depends. Two more systems of equations, one system of inequalities. Tickets to a movie cost $11 for adults and $7 for students. So this time we know the cost per. Oh, I think we did for the fair one as well. A group of family friends purchased 8 tickets for $76. How many adult tickets and student tickets were purchased? Set a system of equations and solve algebraically. I say that because you could totally guess and check this one if you try enough. What if it's 0 adults and 7 students? 1 adult and, or 8 students, I should say. All right, 8 tickets in total. That is adult tickets and student tickets total, right? How many adult tickets, student tickets were purchased? Let's let x equal number of adult tickets. I'll put AC. And let's let y equal number of student tickets, SC. Purchased there. So, 8 tickets total. Adult tickets plus student tickets equals total tickets. And then dollar amounts. This is actually smaller numbers. This is actually a lot easier than the others when it comes to solving eventually. We don't have to say decimals. $11 per adult times the number of adults plus $7 per student times the number of students equals $76 total. Yeah, systems of equations again. Once again, elimination method looks pretty good here. Times -7 per. And I always like to try the smaller one if I can, or the one that's just easier to get to. In this case, it doesn't really matter. -7x minus 7y equals -56. The y's go away. You are left with 4x equals 20. Therefore, x equals 5. It looks like 5 adult tickets were purchased. 5 adult tickets. How many student tickets? Well, 5 plus what is 8? 5 plus 3 is 8. Y equals 3 student tickets. And does that work? Let's double check this one. The numbers are good. Obviously, the 5 plus 3 works. 5 times 11 is $55 spent for adults. 3 times 7 is $21 spent for students. 55 plus 21 is 76. And that's the only combination that gets you to $76 with 8 tickets purchased. That's why in solving for that we do that. There's just one answer. Okay, number 5. In a class of 36 total boys and girls, there are 8 more girls than there are boys. How many girls are there in the class? Set up a system of equations, solve algebraically. Once again, you could guess and check, but let's not do that. This time I'll do, let's do this. Let's do chromosome things. X equal number of girls. I was going to do B and G, but let's let X equal number of girls, Y equal number of boys. For that Y chromosome. All right. When you total the number of people, X plus Y, you get 36 total boys and girls. Now, there are 8 more girls than there are boys. This is a comparison between girls and boys. Here's how I'm going to start this off. I'm going to start off by saying X equals Y. Now, that's not true. X equals Y would mean there are as many girls as there are boys. But I'm going to compare them. I'm going to say to make the number of girls and boys equal, I'm going to have to do this for one of them. Like if it said there are twice as many boys than there are girls, then I would double the number of girls to get boys, things like that. Now, there are 8 more girls than there are boys. What people tend to do is, if this is the number of girls, people tend to do plus 8. But be careful. That would mean that to match the number of girls with boys, you'd have to add 8 more girls. No, we have 8 more girls comparatively. So actually, x is y plus 8. The number of girls is the number of boys plus 8. If there are, this isn't true, but if there were 10 boys, there would be 18 girls. You take the number of boys and add 8. So that's just that comparison thing you have to be really careful with. Anyway, I want to use substitution this time because I have x isolated right here. I can take y plus 8 and substitute it for x in this equation right here and solve, where I will now have something that says y plus 8. That's an expression for the number of girls in the class represented as boys, plus y equals 36. This took x's place, and there's the plus y equals 36. Combine like terms, subtract 8 over, 2y is 28, and divide, you get y equals 14. There are 14 boys in this class. How many girls? X plus 14 equals, well, actually, there are 2 different ones. Let me do the other one, actually. X equals 14 plus 8. X equals 22. 22 girls. So does that work? 8 more girls than there are boys? Yes. 22 girls versus 14 boys. Does 22 plus 14 equal 36? Yes, it does. Okay, last problem here. This is a system of inequalities one. I'm probably going to have to move myself. So let's do that. And we'll answer those questions later. You can work a total of no more than 10 hours each week at your 2 jobs. Your jobs are house cleaning and babysitting. Okay. House cleaning pays $5 per hour, and your babysitting job pays $8 per hour. You need to earn at least $56 each week to pay your bills. Write a system of inequalities that shows the various numbers of hours you can work at each job and graph. So in this case here, there's not just one answer. There's a multitude based off working no more than 10 hours. And you want to make at least $56 per week. So I can work, if it was possible, I'd love to work 2 hours and make $100. That would be very ideal. I don't know if that's possible in this scenario. That's unlikely, but we'll figure out what that situation is through a graph. We're not just solving one answer. We're not using elimination substitution. We're using graphing and the shading thing for this. So we're going to have 2 different equations, one based off our hours and one based off our money collected. Now, we set things up kind of similarly, but with an inequality. You work a total of hours from house cleaning and babysitting. If X is the number of hours house cleaning, and y is the number of hours babysitting, and you add those, that will compare to 10. Does it equal 10? No, you can work a total of no more than 10 hours. We can work up to 10 hours or less. So we can work, the total amount has to be less than or equal to 10 hours worked. So here's an hours inequality. Then we'll have another inequality based off the amount of money that we make for both of them. House cleaning pays $5 per hour, so if I can make $5x from that. $5 per hour times the number of hours house cleaning. $8 per hour from babysitting. So 8 times y is the number of amount of money I make babysitting. And I want to make more than $56, or at least $56, more than or equal to. The amount of money I make must exceed or match $56 here. This is our system of inequalities. There are 2 others that we could ideally write. Basically, our hours has to be greater than or equal to 0. This is one of those assume that this is true kinds of things, but sometimes they ask you to write that kind of stuff, right? You can't work negative hours. But all that's going to do is restrict us to this first quadrant right here when it comes to graphing. So what I'm going to do is I'm going to graph these 2. And in order to graph them, I think what's best to do is write these in slope-intercept form, at least the bottom equation right here. Let's get y by itself right here by subtracting 5x over. Oh, not equals, greater than or equal to. Y is greater than or equal to mx plus b form. And then dividing both sides by 8. Y is greater than or equal to negative 5, greater than or equal to negative 5/8 x plus 56 by 87. So this is one of the ones I can graph here. You have a y-intercept of 7, and you go down 5 over 8, like this. And that's really as much as I can fit there. What I'm going to do is draw myself a straight line. It will be a solid line because it's also equal to, not just greater than. And then my shading for this, it needs to be greater than or equal to this. So I want to shade above this curve right here. The shading represents my solution set for all of the hours I can work that will keep me at or above $56 earned. That's what this shading is telling me. And that's what the line's telling me as well. If I get a point that's on that line, that's exactly $56 earned. If I get anything that's above this line for hours worked, this will get me more than $56, which is cool. You're like, okay, well, just work more. You'll make more money. That's true. Or you're like, well, just work babysitting. I guess I got to do some house cleaning as well. But you're like, just do this, just do that. You just got to remember that I can only work up to 10 hours. So that's the other part right here that I did not yet graph. This one right here, I'll just go and mark it in green. X plus Y has to be less than or equal to 10 right here. This is in standard form, your X and Y intercepts are 10 each, 10 and 10. To meet these kind of hits these points in between right here. So basically my line is going to go right through here. I'm going to go and draw that in a moment. Boom, 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 boom. And it's also a solid line because I can be on the line itself like that. Only now this one has to be shaded below, because the idea of this one is I can only work up to 10 hours, and anything on the line is exactly 10 hours worked. Anything underneath this line is less than 10 hours worked. Now, ultimately, what you're looking for is the overlapping shaded region, which is the solution set to both. Things that are on the solid lines and things that are in the overlapping shaded region of each. What's just green or just blue isn't enough. What we need is what's here in whatever color that we made in between. I'm going to go ahead and kind of, this red. This red is the overlapping shaded region right here. Forgive me for that. Let me make it a little lighter. Let me do like a purple as well. The overlapping shaded region right here is the only set that we can do, which satisfies 10 hours worked or less and $56 made or more. I guess that looks a little too close to the other bluish. So anything within here would work. Here is our graph. That means I could work 1 hour babysitting, or excuse me, house cleaning, I think, and $8 and 8 hours babysitting, and that would satisfy both of these. Can you house clean 5 hours and babysit 4 hours? House cleaning is X. Can I house clean 5 hours and babysit 4 hours? As long as everything's drawn to scale, and that makes it pretty close, right? Pushing it pretty close as far as, is your drawing accurate enough for this? But as long as it's within the shaded region or on a solid line, and it's actually in the shaded region, the answer is yes, you can. If it was outside of it, the answer would be no. So there's more than one answer to this, right? There's an infinite number of answers within here that you can do, and then there are so many that you can't do outside of it. Okay. And that's the systems of equations and inequalities in a nutshell, or at least enough that I'm going to do there. I'm going to keep moving forward, and let's look at exponential functions and models. So these graphs, at least just in integrated math 1, we are only going to be graphing in the form y equals a times b to the x power. There is no h and k horizontal, vertical translation stuff. We'll just work off here. If there is no translation, then a represents your y-intercept. That is the point that crosses the y-axis when x is 0. The y value is a, pretty straightforward. B represents what's called your growth or decay factor. That's what we multiply by each time to increase or decrease our y values here. We're going to graph all of these, including the asymptote. We're going to plot some points. Okay, this number 1 right here. This is y equals ab to the x power. You can tell that a is 6 and b is 1/2 right here. Now, there are 4 different kinds of graphs that can occur. This is among one of them here, based on a being a positive number and b being a value between 0 and 1. This is what is known as positive exponential decay. What's going to happen is we are going to start with a positive value, 6. Your values will remain positive, only as we keep multiplying by 1/2 over and over, the values will start shrinking. That's why it's known as decay there. Now, the y-intercept is the 0, a. That makes it 0, 6. We'll talk about the range in a second, but the domain is all real numbers. Basically, it means I can substitute any value for x in this equation, and I will always get a value out for y. No matter how big or small, at least there is a defined value on the set. Fractions, negatives, infinity, negative infinity, 0, any of them. But we'll talk about the range after we see the graph. Like I said, this is positive decay. This is because a is greater than 0, but here b is between 0 and 1. Note that b cannot be negative in exponential equations. B would not be 0 or 1 either, for reasons you'll hear about in a moment. So let's go and start graphing this. We're going to start on the y-intercept of 0, 6 right here. And the way that exponential functions work, or exponents work, is if an exponent describes how many times you multiply by 1/2, notice we don't multiply by 1/2 at all when x is 0. We do once when x equals 1. When x equals 1, you multiply 6 by 1/2 once. 6 times 1/2 is half of 6, which is 3. 6 divided by 2. Then you take that number, you multiply by 1/2 again, right? If x is 2, it's 1/2 squared times 1/2 times 1/2. So you take 3 times 1/2, which is 1.5, or 3/2, times 1/2 again. If I want to do 3/2 times 1/2, that's 3/4. You're basically doubling your denominator, which is, it's taking half your value, but it's doubling the denominator. 3/4, 3/8, 3/16. You can see how it just shrinks over and over and gets closer and closer to 0. Never actually hits 0, but it gets closer to it. That's where we start approaching what's called a horizontal asymptote, a line which shows we do not touch or cross, we just get closer and closer to. And our asymptote on these will always be on the x-axis, y equals 0, as long as there is no, +7 kind of vertical translation here. And these are some of the points on the graph. Let's go to the left a little bit. We had to take half of something to get 6. That means we double that 6. That's 12. It's basically dividing by 1/2. And if we doubled 12, we would get 24. That's way up here, kind of off the graph. So this is quite a bit here to do this for this graph right now. Let's go ahead and draw its graph as best as possible. This is an exponential function. It's not a parabola. It's not a quadratic. It's not a U shape. It'll just keep getting closer and closer to the asymptote there. Not actually hitting. Even if it looks like it's simulating and getting closer to hitting there. And it takes off in this direction. Probably more so like that, I'd say. So I'll go and do that. Because it never quite hit -2 yet, right? Okay, there's the graph itself. Now, I didn't yet answer the range question. The range question being, what y values exist here? Based on the x values you plug in, what y values are possible? Well, it's not possible to get 0, even though you'll get really close to it, and it's not possible to get negative. And you seem to take off toward positive infinity. You hit every positive number under the sun. You just never hit negatives or 0. So the y values must be greater than 0. And that graph can kind of help assist you with that, or at least the knowledge of what exponential functions look like as graphs. All right, number 2. G of x equals -4 times 2 to the x power. So this time your a value is -4 and your b value is 2. The y-intercept is at 0, a, so 0, -4. Let's plot that point now. You notice that this will be a negative function here. It'll stay negative. We're just going to be multiplying or dividing by 2, a positive 2, and multiplying a negative by a positive will keep it negative. So it's going to stay negative. You can tell the graph is already kind of supporting us with that notion. We're going to stay underneath the x-axis. Now, is this growth or decay? Well, hold on. A is less than 0 here. Is it growth or decay? Well, the b value is greater than 1 here. This time we're multiplying by 2 over and over. And you'd think that's growth, and it is. But look at what happens when we graph this. Just be careful. -4 times 2, as x increases by 1, is -8. -8 times 2 is -16. And you can see that we're going down. Now, does going down mean that it's decay? Actually, no. The negative instance, it being negative lets us know that we're going down, or the other way around, right? You'll be going down when it's negative regardless of direction. The question is, are we growing negatively? And the answer is yes. This is negative growth because b is greater than 1. As long as b is greater than 1, it's growth. As long as b is between 0 and 1, it's decay. Doesn't matter if it's the other way. See, this is going more this way. Negative decay would look like this. Even though the numbers go higher, they're shrinking closer to 0, and that's a different thing. So if we're multiplying by 2 going this way, we are dividing by 2 going this way. -4 divided by 2 is -2. -2 divided by 2 is -1. -1 divided by 2 is -1/2. Half of that's -1/4 and -1/8. And you can see the asymptote approach, just like last time. We're getting closer and closer to y equals 0, the x-axis there. We never actually hit. So we'll get to that domain and range aspect in a bit there. But here's our graph as we take off down in this direction here. Whoops. And forevermore downward. Now, domain, once again, is all real numbers. For our exponential functions, there is never a limit that we should have on x. No matter what I substitute, I will get a valid value, even if it's super huge or super small. The range, however, seems to be only negative numbers this time. Our y is less than 0 because we are now below the asymptote this time. Give me a second. And there is this graph right here. So why can't b be 0 or 1? Because if you multiply by 0 over and over, the number just stays as 0. That's not exponential. Why can't b be 1? If you multiply by 1 over and over, the b value just doesn't change. It's not 0, but it's just -4 over and over. Also not linear. Why can't it be negative? Well, it's not an exponential function that way. It would oscillate sign every time you increase x by 1. You'd go from a negative to a positive to a negative to a positive. But there's also no real in-between, because raising negative values to fraction exponents can lead to undefined values. So there's no negative either. B is either between 0 and 1, or it's greater than 1, and that's it. Okay. We are going to have two, I think on this side and on the other side, there are two exponential growth decay models, whatever, what have you. And here's your formula. If you want to find out your output, you take some initial value, some original, kind of like a y-intercept, if you will, based on time 0, whatever your time is referring to. And this 1 plus or minus r to the t power, basically substituting things in. R is your percentage growth or decay, increase or decrease, but you got to make it in decimal form. The 1 represents 100% here, and you increase with 1 plus r, you decrease with 1 minus r. You'll see it with the substitution. We'll make it make sense. All right, let's write an exponential function here. Well, actually, we have one this time. After an explosive weekend, opening weekend box office for Spider-Man No Way Home, the subsequent weekends followed a predictive box office pattern modeled by this, where T represents the number of weekends the film has been out, and Y represents its box office in millions of dollars for any given weekend. That means that 215, this number means $215 million, not just $215. All right, is this exponential growth or decay? What's the average percentage loss per weekend? Well, hearing loss, that must mean it's decay. But why is it decay, really? Because this is y equals ab to the x power, and b, the growth or decay factor, seems to be a number between 0 and 1. It's between 0 and 1, so it's decay. Every time you multiply by a fraction or decimal less than 1, your value is lessening, right? Something times 0.72 becomes something smaller. What is the average percentage loss per weekend? Now, you look at that b of 0.72. That does mean 72%. It means that whatever value you had before and you multiply by 0.72, you're going to be taking 72% of the value. Like, it's going to be smaller. It's going to be not 72% smaller, but 72% of it. How much smaller is that, though? How much smaller is 72% compared to your full amount, your full 100%? You take 100 minus 72, and that gets you 28%. It's basically 100 minus 28 is 72. You're taking 28% off of whatever number you had to get there, right? 28% drop from the previous weekend would get you there to 72% of. Like if you have a sale that's 40% off of something, that means you're only paying 60% of the amount, 100 minus 40. So that's kind of the way to look at it, the average percentage loss. What's the predicted box office for its 11th? This was at the time when I delivered this kind of review or this test to my kiddos. It's no longer upcoming. But for the 11th weekend, what's the predicted box office? Not including something like Martin Luther King weekend or where something else happens like that, just the normal one. And actually got really close to the actual prediction, within like $10,000. But y equals 215.35 times 0.72. T represents the number of weekends it's been out, so this would be for the 11th weekend here. So if I take 215, let me use this calculator for you this time. If I take 215.35 and multiply that by 0.72, raise that to the 11th power, I would do it all in one fell swoop. Do not do 215.35 times 0.72 and then raise that answer to the 11th power. We got to make sure it raises this to the 11th power only. We multiply by 0.72 11 times. We take 72% of our value and then 72% of that value and 72% of that value 11 times. That's what we're looking for. So this answer is 5.805. I'm going to write 5.81. 5.81. Now, what does that represent? Is that dollars? It's $1 million. And it's already kind of pre-written. $5.81 million on that weekend. Okay. Now, the movie's not losing money, right? The movie's gaining money. You take however many in one weekend, add it with the other week. Actually, you add it for the whole week, but this is just over the weekend itself. you add them with the previous weeks, but this is how much it made on this particular weekend. It's making less per weekend, right? As it, 72%, 28% less, but 72% of. But it keeps going like that. Anyway, I can't remember what the actual, yeah, that's the number. I can't remember what the actual value was in reality. All right, here's a true statement. You can look him up. In 2014-2015, Mr. Robinson taught a student named Kelly Wakasa. He began a YouTube channel that took off a few years ago. His channel, this isn't current anymore. He's near 1 million. His channel currently has 868,000 subscribers, and this number is now increasing 1.2% more subscriptions per month. I might have made that up. After how many subs will Kelly have after 1 year? So this time we have to come up with the model itself. Now this doesn't matter itself. This is just a factual statement. Hi, Kelly, if you're watching. Okay, so he had 868,000 subscribers to start with. If we're looking, not to start with, but to start this model. If we're looking at this formula right here to use, we want to find out how many subscribers he has after T months in a situation. So we can write out y equals, he starts out with this many in the model. He is increasing his number of subscribers. This represents R, but you got to take that decimal and shift it 2 places to the left right here, or this percentage and shift it 2 places to the left to get the decimal. So we are going to do 1 plus 0.012 to the t power. So the model is y equals 868,000 times 1.012 to the t power. So that's the model representing Kelly's subscription base, of which I am a subscriber, and you guys should subscribe as well. He has fun content. All right, after 1 year, you have to remember that 1 year, the t is number of months. So 1 year is 12 months. T equals 12 in that scenario right there. So in terms of solving this, we are going to substitute 12 for t. Y equals 868,000 times 1.012 to the 12th power. So if you don't mind, I'm just going to go ahead and type it in this calculator very fast. And I'm getting about 1001580.5. So 581 subscribers. That is comma. That's just a little over 1 million. Just a little over 1 million subscribers there. So let's hope that ends up being the case very soon. I think he's getting very near that for himself. That's awesome. I'm looking forward to hearing about that. In fact, let me look up this day. Today is May 30th when I'm recording this video here. You won't see this on the screen. He is currently at 992,000 subscribers. I'm here for his 1 millionth subscriber party, whatever it is. All right, but that's the answer though. Okay, number 5, match the equation in y equals ab to the x form that likely corresponds with each exponential graph pictured below. So here, this is graph A, graph B, graph C, and graph D. And my picture's kind of in the way, but here are 4 equations representing. Now, if you can tell, each of these 4 graphs, just without the equations, each of these 4 graphs represent something in particular that we have. This is what's called negative exponential decay. Negative because we're underneath the asymptote, decay because it shrinks toward the asymptote. This is positive exponential decay, as we're above the asymptote but shrink toward it. This is positive exponential growth, above the asymptote and taking off, and negative exponential growth. Right there. So in order to have these, negative exponential decay would have to mean negative. Your a has to be less, in y equals ab to the x form, a would have to be less than 0, and b would have to be between 0 and 1. Give me 1 second here. B would have to be between 0 and 1. We're going to find the graph that matches that. For positive decay, a would have to be greater than 0, where b is between 0 and 1. For positive growth, a would have to be greater than 0, b would have to be greater than 1. And negative growth, a less than 0, b greater than 1. So which one has each of those? That's what we're going to find. Which one is a less than a negative a number and a fraction or decimal b value? A negative a, no, yes, yes. Which one has the fraction b value? This one. This must be graph A. Y equals negative 4 times 1/2 to the x. Basically means that this is 0, negative 4 right here, and then you take half of that, each time x increases by 1. So that must be graph A. Graph B, positive decay, a positive a value, and then a fraction thing that looks like this one right here, graph 8 times 1/4 to the x. Must be that, like y-intercept of 8, and taking a quarter of it each time. Graph C, positive and greater than 1. that looks like this one right here. Y equals 3 times 2 to the x. You double the 3, you double that number, 6, you double, etc. And that leaves us with D right here, negative growth, negative exponential growth. It starts at negative 5 and then doubles and doubles and doubles right there. And those are the ideal matches. All right, number 6. What is the decimal equivalent of 1.2%? We just saw this for the Kelly-Wakasa thing. You take the, let me write this. You take the 1.2 and you shift this 2 decimal places to the left right there. Insert it yourself a 0. So it's 0.012. Like that. Best way to write it. What is the decimal equivalent of a 25% increase? If you keep in mind, an increase would take the 100% of something and add 25 to it. That's 125%. The decimal equivalent is 1.25, like so. What you could also do is the same way as you saw it in the equation form, 1 plus 0.25, right? And that gets you the 1.25. 1 is the 100%. That's the decimal equivalent right then and there that you're working out. Third one, kind of multiple choice here. What is 0.87 equivalent to? Notice there's no percentage symbol on it. So 0.87 means 87%. We just saw something like this from the Spider-Man No Way Home example. 72% was a 28% loss. 87% means a 13% decrease, like that. You take 13% off 100% and you get 87%. And here's the decimal equivalent to that, right? So that's kind of what that thing means there. It's not an 87% decrease. That would mean taking 87% away from 100%. That would be much smaller. And 0.87%, no, that decimal equivalent is 0.0087, not the same thing. So the answer is a 13% decrease here. Lastly, number 7, simplify 4 times 2/3 to the negative third power and write the final answer as a mixed number. Reduce the fraction if possible. Well, I'm going to start with this. A negative exponent means you place a numerator into the denominator and vice versa if they're both raised to the negative exponent. Change them positive. So that becomes 4 times 3/2 cubed. I'm going to go ahead and cube the 3 and cube the 2. That leaves me with 4 times 27 over 8. Instead of doing 4 times 27, let's do 4 divided by 8. That reduces to 1 over 2. So that gets us 27 over 2, which cannot be reduced. As a mixed number, that is 13 1/2. 2 goes into 27 13 times with a remainder of 1. So the answer is 13 1/2. That was for graphing. You notice at the times when I talked about 3/2 for that first graph, I was saying like, hey, what's 3 divided by 2? That's 3/2 or 1 1/2. That kind of helps you come up with those numbers there. But it's kind of just placed at the end and working exponential properties such as negatives. Okay, that's the exponential review that I have for you guys there. Everything else, if there's algebra, it's basic in the form of like, linear, solve for x, just get it by itself thing. No quadratics here and there, no systems of equations. Everything else is as geometry based as can possibly be, except for some parallel lines. I take it back, there's some parallel lines bits. I haven't done those for my kiddos, but I'm going to do some here in this video. Now, this is all mixed review. They come in different droves. You'll see things not repeat themselves question-wise, but you'll see material repeat itself. This isn't the only time that we'll talk about congruent triangles, for example, on number 1. By the way, I don't think there were congruent triangles proofs here, not really to the full extent. If you want to find some, my Integrated Math 2 video has some, and in the description section, it notes where those proofs actually are, the geometric proofs. All right, we got a bunch of problems to do here. Let's go ahead and get going. And we are, how far into our video now? 48 minutes in. Let's see how we go. If triangle PQR is congruent, good start. If triangle PQR is congruent to triangle XYZ, name all congruent corresponding angles. Well, the important aspect about congruent triangles is in the triangle congruence statement, which we'll be talking about a lot in this video, the letter order matters. This is letter 1, 2, 3, and letter 1, 2, 3. When that's named, it's not because they're alphabetical, that was their choice, or it's just how the triangles were. But when it's named as such, that means the letter order corresponds to that part in that triangle. The part for P corresponds to the part for X. That could mean they're angles, like angle P would be congruent to angle X, which is exactly what we're looking for here. And it could talk about segments or diagonals or whatever as well. We'll get into that. Angle Q is congruent to angle Y, therefore. And angle R is congruent to angle Z. Those are the third letters for each. So those are the congruent corresponding angles. Now, if you want to draw something like this out, let's say I had this triangle and this triangle here. Let's say this was our PQR and our XYZ. And I'm going to draw them the same direction to keep things easy. Angle P is congruent to angle X, angle Q is congruent to angle Y, angle R is congruent to angle Z. And you can see that. Now, what I want to show you with this is the congruent corresponding sides. Notice how PQ corresponds with XY in the way that I drew them the same, in the way that whatever. Those are corresponding congruent segments. You can see those are letters 1 and 2 with letters 1 and 2. So they still correspond by name. You don't necessarily need the drawing to understand that. But that can help support what it is we're talking about. So segment PQ corresponds with segment XY. And that's how we write out segments. Now QR corresponds with YZ. Notice QR corresponds with YZ. Segment QR, excuse me, with YZ, congruent. And, let me just mark those up. And apparently PR and XZ. Now when you look at the segment names, PR is 1, 3, XZ is 1, 3. Even though they're not next to each other here, they do connect, right? They do connect as a triangle. PR is congruent to XZ. The important aspect here is what's called CPCTC. Corresponding parts of congruent triangles are congruent. The triangles are congruent, so their corresponding parts are congruent. What are parts? Angles and sides. 3 corresponding congruent angles, 3 corresponding congruent sets of sides. 6 parts total in triangles. So if you can prove triangles are congruent, that would lead to corresponding parts congruent. Notice we're not talking about triangles suddenly anymore. Name the 5 ways to prove a quadrilateral is a parallelogram. I'm going to list out these things. I'm going to type them out for you. Okay. So the first one, and this is the definition of a parallelogram. Opposite sides of a parallelogram are parallel. The second thing is, and this is a property, opposite sides of a parallelogram are congruent. The third thing is opposite angles in a parallelogram are congruent. I should really show you my property toolkit that I made for my students. Consecutive angles are supplementary. I'm going to draw these out in a second for you. And the fifth one, I don't know where I can list it here. Let's shrink this some. Statement 5 is the diagonals in a parallelogram bisect each other. Okay. Now, what does this actually look like? Here's a parallelogram, all right? Now, in this parallelogram, the opposite sides, like I said, are parallel. That is just the definition of parallelogram. Parallel, parallel. Not only are they also parallel, but they are also congruent to each other. Boom, boom, with boom, boom. Now, you could actually prove this using some congruent triangle bases. I'm not going to do that here. It might show up in these later. Congruent triangle, CPCTC, all that stuff. Opposite angles are also congruent. That means this is congruent to this, and then this is congruent to this. You can kind of see it kind of looks like that. Consecutive angles are supplementary. I don't have a way of really marking that other than if I put like an X and a Y that shows that X plus Y is 180. If you notice, this is 2 parallel lines cut by a transversal. These are same side interior angles, which are supplementary. Something we get to talk about more later. And lastly, the diagonals bisect each other. Now, let me kind of draw diagonals there. Kind of cuts into my X. Diagonal and diagonal. The diagonals bisect each other. That means that this diagonal breaks this one up into 2 congruent parts here. And this diagonal breaks this diagonal into 2 congruent parts here. Now, the diagonals aren't necessarily congruent to each other, which they're not. This diagonal is clearly shorter than this one here. And they're not necessarily perpendicular to each other, nor do they bisect the angles. You can see that angle looks smaller than this one here. And by and large, it probably is. But those are what those 5 features mean right there to show that it's a parallelogram. Okay, besides a rectangle being a parallelogram, what are other features of a rectangle? Now, the first statement they're making there is, notice this rectangle I'm going to draw right here. A rectangle is a parallelogram. It's just taking a parallelogram and skewing it kind of upright, right? You see this parallelogram right here, and just take the things and like that. A rectangle is a kind of parallelogram, which means a rectangle has all 5 of these properties as a part of what it does. There are just other things that it has on top of it. What else do you know about I can't really fit anywhere. What else do you know about a rectangle besides what the parallelogram had? Well, it has all right angles, all congruent angles, which are right angles. Notice how the opposite angles are still congruent, and consecutive angles, 90, are still supplementary. 90 plus 90 is 180. But they're now also all congruent to each other. They're all right angles because that's what a rectangle is. But a quadrilateral's interior angle sums 360 degrees. Divide by 4, they're all 90. Now, a rectangle also has, let's see, what other features? It also has two congruent diagonals. So while the diagonals still bisect each other, that's great. The diagonals themselves are also congruent to each other now. So once it tilts itself that way, notice how I said this was shorter than this one? Well, now these are the same length here. So what are the two different features of a rectangle there? We have all right angles, which is kind of the definition of the rectangle. And then diagonals congruent to each other. So those are the two that a rectangle specifically has. All rectangles are parallelograms. Not all parallelograms are rectangles. They could be. They don't have to be. That kind of thing. And the third one's the rhombus. Besides a rhombus being a parallelogram, what are other features of a rhombus? I don't know if I have a rhombus tool. I don't, just another parallelogram thing. Let's try and make one as rhombus-like as possible. Now, rhombus is a parallelogram with all congruent sides. I'd say I'm getting close to the look right there-ish. Oh, man. I'll try with that. Okay, rhombus is a parallelogram with all congruent sides, and I'm rotating it to really show you that look. I'm getting closer to the look right there. So it is a kind of parallelogram, right? Like this one. But now we shrink those sides inward. Now I rotate it into this diamond configuration to give you a little different look of that look, because I want to show you what the diagonals do with it. Not only are there all congruent sides now. Remember, opposite sides are still parallel. Opposite sides are still congruent, obviously, but now all are. But here are the other two things. Diagonals are now, this isn't a perfect drawing, sorry about that, but the diagonals are now perpendicular to each other. They don't just bisect each other. They're now perpendicular to each other as well. And they now bisect their angles. This angle is congruent to this angle. This angle is congruent to this angle, etc. Not a perfect drawing, but opposite angles are still congruent, and then diagonals now bisect those angles. Now, unlike a rectangle, because this was not a version of a rectangle, right? This was a version of a parallelogram. Unlike a rectangle, the diagonals aren't necessarily congruent. That looks shorter than that still. And we don't necessarily have right angles. So a rhombus has different things than a rectangle does. So rhombus has, besides being a parallelogram, besides those top 5 things there, it has all congruent sides, diagonals perpendicular to each other, and then diagonals bisect their angles. Sorry about the clank. It's kind of, my keyboard is out of the way for my microphone, and it's kind of in a weird loose spot. All right, what are the characteristics of a square? Let's just name the ones that define the square as opposed to everything, because here's the thing. Square has all of these things. A square has opposite sides parallel and congruent. Actually, it has all sides congruent, by the way. It has not only opposite angles congruent and opposite angles congruent, consecutive angles supplementary. It has all angles congruent, just like the rectangle. Diagonals are congruent to each other, bisect their angles, and are perpendicular to each other as well. Everything that you have for all of these here are all true for the square. But the two main things for the square is basically the descendant of the rectangle and the rhombus. The rectangle, by definition, is all congruent angles. The rhombus has all congruent sides. Characteristics of a square has all congruent angles and sides. The angles are specifically 90-degree angles, too. Right angles and sides, just like a rectangle. The square is that ultimate quadrilateral that has everything true about it that you can have. There's my square. I'm just drawing all over the place. Here's my square. Right angles, congruent sides, and therefore everything else is true. Opposite angles congruent, consecutive angles supplementary. Diagonals congruent to each other, perpendicular to each other, bisect each other, and bisect their angles. all congruent there. Like 45-degree angles, even more specifically, right? We know they're always 45-degree angles. And there's your square. We might run into those things later. Okay, enough on that. Not even talking about quadrilaterals now. We'll probably go back to them. In the figure, this figure, name two pairs of vertical angles. Vertical angles are angles that are opposite each other when lines intersect. So here's a vertical angle pair right here. I can call that angle, we name angles with 3 letters if it's ambiguous. SQR is paired up with, right, it's a vertical angle pair. There's not one, it's not one angle is a vertical angle. It's some angle is a vertical angle pair with another. So SQR is a vertical angle pair with TQP. And then we have another set right here with SQT and RQP. Now, what's true? Oh, hang on. They're going to tell right here. What can you conclude about your angles in number 7? The angle pairs, at least. The angle SQR. Vertical angles are congruent to each other. Angle SQR is congruent to angle TQP. And angle SQT is congruent to angle RQP. So they're congruent. Vertical angles are congruent. Using the same figure, name 4 pairs of linear pair angles. A linear pair straight up. Notice this straight angle right here. You might call it a straight line, but notice how it is straight. It's this angle that opens up to 180 degrees. When you cut it with this part right here, you built 2 adjacent angles, SQR and RQP. That's known as a linear pair, this 1 and 2. Angles 1 and 2 right there are a linear angle pair. This angles 1 and 2 are a linear angle pair. This angles 1 and 2 are a linear angle pair. And this angles 1 and 2 are a linear angle pair. Any of these things that make something with a straight angle, two angles that are congruent, two angles that are adjacent and supplementary to each other. Name 4 pairs of linear pair angles. We have SQR and RQP. We have, let me get rid of that purple, otherwise I'm only looking at that line. We have RQP and PQT, right? They make that angle. RQP, that's not a P. PQT, if I said RQT, I apologize. PQT. Angle PQT and TQS. And then lastly, angle TQS and SQR. Sometimes it's easier if they just had angled numbers, right? What can I conclude about Yoru angles? Here's the typo I saw. What can you conclude about your angles in number 8? All of these pairs are supplementary. I'm not going to write and say each one is supplementary, but their measures are supplementary. Excuse me, their measures add to 180. They are all supplementary. So remember that. Linear pairs are supplementary. Vertical angles are congruent. Congruent, set them equal each other. Supplementary, add their measures to 180. All right, what are the endpoints of the image of A prime, B prime, segment A prime, B prime, if segment AB is reflected over the line y equals x? Now, this isn't a very pretty looking drawing when it comes to drawing things to scale. What you'd want to do sometimes is on a grid, reflecting over a line means getting the mirror image across this line. Like, how far away is this from the line here? Well, you reflect it over here and call it A prime. How far away across this side, B prime? The problem is they're not really to scale. They're kind of hard to count here. And I can't really get that perpendicularness to it, right? You want to go straight through perpendicularly to that. So what I'm going to do instead is kind of use the rule, the y equals x rule. When you reflect across this line, what happens is your, if you have some original point at some x comma y, whatever it is, your new transform point reflecting across y equals x is the y and x switch places. If your original a value looks to be at 2, 4, 5, 6, comma 4, if a is at 6, comma 4, then a prime would be at 4, comma 6. That's that transformation. That's what the transformation is. If b is at 4, comma 1, then b prime would be at 1, comma 4. So that's the answer. Let's go ahead and plot those and see if that looks okay. 4, comma 6 is around there. That's a prime. That looks like it kind of reflects there. And b prime would be at 1, comma 4. I probably had that one off a little bit before. And that would be the drawing. If you tilt your head the proper direction, you can kind of see the idea of the transformation. But again, this isn't fully drawn to perfect scale either, so we just make do with what we can. But that's the answer, though. All right, number 12. We have this angle, this diagram right here. The measure of angle JHI is 3x minus 8 degrees. That is this small guy right here, 3x minus 8. And measure of angle GHI is 7x minus 4 degrees. And measure of angle JHG, the entire thing is 68 degrees. Now, generally, this is harder for me to kind of show like this, but I'm going to say, hey, the whole thing is 68 degrees. I was going to put percent. Find the measure of angle JHI and measure of angle GHI. Okay, in order to find those, we're going to have to first solve for x. In order to solve for x, we want to write an expression using what's known as the angle addition postulate to compare or to relate all three of these angle measures together. If you add this angle measure with this angle measure, you will get the entire angle measure. So if we make an equation that says 3x minus 8, the measure of angle JHI, plus 7x minus 4, the measure of angle GHI, that will equal the measure of angle JHG, 68. And there's the algebra equation we're setting up here. These are the kinds of algebra things we're going to have to solve for here and there quite a bit. 3x plus 7x is 10x. Negative 8 minus 4 is negative 12. If I add 12 to both sides, I get 10x equals 80. If I divide both sides by 10, I get x equals 8. Now I'm going to use that x. Remember, I'm not done unless they just said solve for x. Here they don't. They say find the measure of angle JHI and GHI. JHI is 3x minus 8. So if I take measure, hold on a second. Give me 1 second. My cell phone is charged. Hold on. Sorry about that. I kept hearing a vibration in my phone was charging in another room. Now I was just thinking that someone was trying to message me, which maybe they were, but it might have been an alert that my phone was charged, and I don't want to keep it charging forever. Okay, what was I doing? Probably finding a measure. Find the measure of angle JHI. Measure of angle JHI, it is 3 times x minus 8. I'm going to take this 8 and, shove it up my x right there. 3 times 8 is 24, minus 8 is 16. 16 degrees. Now, this actually has units. It's an actual angle measure, so we're going to put degrees for that. Measure of angle GHI. You have a couple ways you can do this. You can do 7 times 8 minus 4, because that's its expression. 56 minus 4 is 52. You could have also used it in the scenario 16 plus the measure is 68. So you could have done 68 minus 16. Right? You'd still get 52 there. Anyway, there's the answer there. And I do know we run across some more of those later, but apparently not right now. Okay, next page, number 13. Write an equation of the line that passes through negative 2, 3 and is parallel to the line with the equation y equals negative 1/2 x minus 7. So the idea is this. We do have the slope of that line, which is negative 1/2. This is y equals mx plus b form, by the way. Y equals mx plus b form. M represents your slope. Your slope is negative 1/2, so the slope of the parallel line to this is also negative 1/2. That's me drawing my parallel symbol like that. I'll do a perpendicular symbol like that sometimes. The parallel line is also negative 1/2. That means this equation will also have a y equals negative 1/2 x setup and then a plus b. We don't know what y-intercept this one will go through. This one crossed through negative 7, and at x equals negative 2, it probably has a different y value than 3. What is this one going to be right here? We have to substitute negative 2 for x and 3 for y to figure that out. And we'll say 3 equals negative 1/2 times negative 2 plus b. Negative 1/2 times negative 2 is 1. So 3 equals 1 plus b, or b equals 2. So this equation will be y equals negative 1/2 x plus 2. That is the y-intercept of this one right here. This one had y-intercept of negative 7. This is y-intercept of 2. They're both parallel. They're both parallel to each other like that. All right, write an equation of the line that passes through 5, negative 2 and is perpendicular to the line 5x minus y equals 2. In order to do this, what you want to find is the slope of this equation. So you probably want to get it in slope-intercept form. You want to make sure it's in y equals mx plus b form. Currently, we have 5x minus y equals 2. Let's go ahead and subtract 5x from both sides. And then let's divide both sides by negative 1. We get y equals 5x minus 2. So here's the equation of this line right here. That means the original slope is 5, or 5 over 1. The slope of the perpendicular line is going to be negative 1/5. You take the opposite reciprocal of this. You flip the fraction numerator denominator and you change the sign. Up 5 over 1 looks like this, whereas down 1 over 5 looks like this, and you can see how these lines are perpendicular to each other right there. So opposite reciprocal slope is needed. So now we know our equation is going to take on the form y equals mx plus b. We just got to now find out what this b is right here. So we're going to do the same thing as we did before. It took a little bit more work to get here, but here's our xy, 5, negative 2. We have negative 2 for y equals negative 1/5 times 5 for x plus b. That'll give us negative 2 equals negative 1 plus b. Add 1 to both sides, you get b is negative 1. So our equation, with multiple different colors that I've used so far, is y equals negative 1/5 x minus 1. This thing is perpendicular to this line right here, and it'll pass through this very specific point. Okay, number 15, compare measure of angle ABC and measure of angle CBD. So they're saying compare this angle with this angle right here. And I'm not marking them congruent, I'm just indicating what they both are. Now, I don't know why this angle ventures off in this direction here. I can make some presumptions about it for you and tell you something about it. Let's even assume for a second this was straight across, and then I'll tell you something about it if it's bent as well. The idea here is all other things being equal in these triangles that we can have, which I'm not going to say by HL here, because it's not a right angle technically, right? It couldn't be. I guess that's why it's bent. But the idea here is that if this was a right angle right here, well, you know what? I can't say it's straight. I'm sorry. Let me reset this. This 5 is more than 4, and these are both lengths of 6 right here. In order for this 6 to go down to this 4 that's bending and matching, 6 needed to close itself inward more. But more importantly, 4 is less than 5 in that scenario. 4 isn't bending upward right here for this to widen out. Opposite a smaller side should be a smaller angle. All other things being equal. And the things being equal, I should have ignored the right angle. The things being equal are 6 is equal to 6, and this length is equal to this length for both triangles. Let's say that this length was 3. I don't know if this length was 3. Then the 5 compares to the 4, and that the 5 is relatively bigger than the 4, so that angle opposite the 5 will be bigger than the angle opposite the 4. That's basically what I'm trying to say. Yes, I guess that could not be a right angle in that case. So, what does that mean? Here's the measure of angle ABC. That is smaller, less than the measure of angle CBD, because opposite a shorter side is a smaller angle. Now, it's true in the other direction as well. All things being equal, such as these two are equal to each other, and this is equal to itself right there by the reflexive property, opposite these two angles are two different sides, a 24-degree angle and a 26-degree angle. So, this side has an angle that's shorter than it opposite, so this is a shorter side, and this angle is a larger this side has a large, I can't speak, I'm sorry. This side has an angle opposite that's larger, so this is a larger side right here. So comparing XB with ZB, XB is shorter than ZB. Compare KG and KP. Okay, again, we have two things being equal here, equal, and then equal. Now we got to compare KG and KP right here. These are opposite these angles. Opposite KG is this angle 70 degrees. Opposite KP is the angle 87 degrees. With all of the things being equal, this thing widens out more. That makes KP larger than KG. So KG is smaller than KP lengthwise. And compare measure angle 1 and measure angle 2. Again, all things being equal, 8, 8. Reflexive properties show that being the same. 5 is less than 9. Therefore, measure of angle 1 is less than measure of angle 2. Angle 1 is less than measure of angle 2. We're not getting the exact side lengths and angle measures for you guys. We're just comparing how they are based on what's there. Now, this is a little misleading. 1 and 2 are not degree measures right here, but these are actual lengths. This is 5 units in length, 9 units in length. These are just labels for their angles, and these are actual measures themselves. So that's a little weird. Sorry. Okay, that's those ones. Okay, number 19. In the figure, angle T is congruent to angle W. Angle T is congruent to angle W. And VU, segment VU is congruent to segment VX. State which triangles are congruent and why. So we can do a proof without needing to do the documented 2-column proof format. What we can show here as a result of this is that these two angles are congruent to each other right here because these are vertical angles. We just mentioned before all vertical angles are congruent to each other. Vertical angles. Something where I'd say is angle UVT is congruent to angle XVW, something like that. So these two triangles are now congruent to each other. There is something called, and I think there's I remember there's a question later on multiple choice, multiple selection. What triangle congruent statements can you use? And angle side is among them. Angle side with angle side. It's a way of saying there's a minimum number of parts that you can show to be congruent in a certain sequence to guarantee that the rest of the corresponding parts of the triangle are congruent, and this is one of them. By angle side, and that's one of them. I'll write out the others in a second. By angle side, I can say that triangle TUV is congruent to, here's where corresponding parts matters, TUV with, it looks like a WXV. You have to go from the single arc mark here across the unknown to the single tick mark down to the double. Across the single arc mark to the unknown, down to the single tick mark to the double. Triangle TUV congruent to triangle WXV by angle side. Now I chose the order right here. You can choose whichever order for your first one if it's not preordained for you, and this actually happens to be alphabetical as well. After that, you just have to make sure parts correspond. Now angle side is an option, and this was the option to choose here. The other options possible are side. That can lock your triangles into two congruent ones. Side, angle. There's angle side, which I just did. And then HL, that's used for right triangles. Hypotenuse like. HL's hypotenuse like. Now this was not angle side angle because we would have to skip a side and an angle to get to that side. Angle side means two congruent angles and the side outside of it. Angle side angle would be something like this. Angle side angle right there. Now, I didn't set a statement beforehand with all this stuff and say how fast I'd kind of be with these. I know a lot of these might sound pretty fast to you. I got a lot to get through. This is an hour 17 in so far. And I don't know if I'm still on the first review worksheet. Yes. I know I did some other things before it, but you know, these will take some time, so I want to make sure that after I'm teaching things with the assumption you've heard them before. This is a final review, not a first time review. So if it seems like I'm going a little fast, it's under some assumption that you've heard some of it before. All right, find the slope of the line parallel to this equation here. Now this is no longer y equals mx plus b form. Just find the slope of the line. This is point slope form. This is y minus y1 equals m times x minus x1 right here. M is your slope. So the slope of a line that's parallel here would be 5, or 5 over 1. All right, 5 over 1. That's fine. Find the slope of the line that's perpendicular to this line right here. Once again, like before, you'd want to get this first into slope-intercept form right here. Get y by itself. So I'm going to write it this way. 3y minus 7 equals 5x plus 2. Let's add 7 to both sides. We'll get 3y equals 5x plus 9. And then I'll divide both sides by 3. Y equals 5/3. X plus, I think, 3. The 3 doesn't matter. What does matter is this 5/3 here. The original slope is 5/3. So the perpendicular slope is the opposite reciprocal slope. It's negative 3/5, like that. Okay. Number 22. In the figure to the right, segment array BX bisects angle ABC. Measure of angle ABC, the whole thing is 5x plus 18 degrees. 5x plus 18. And the measure of angle CBX, just the little guy, is 2x plus 12. Find the value of x and measure of angle ABC. ABC being the whole thing. So, okay, these definitely aren't, before I speak on that, the bisector divides this angle ABC into two congruent parts. That means that measure of angle ABX is equal to the measure of angle CBX right here. Measure of angle ABX is equal to the measure of angle CBX. Well, we know the measure of angle CBX is 2x plus 12. That means the measure of angle ABX can also be written as 2x plus 12. And that's important because I need to find it. I'm going to use my angle addition postulate. If I add this angle with this angle measure here, I get the measure of the entire thing. So if I double my 2x plus 12, add it to itself or double it, I get 5x plus 18. I was going to initially say this isn't equal to this because I have to add these two together right here. These two are equal to each other, or double them up, however you want to put it. I'd like to distribute one for now, though. 2 times 2x is 4x. 2 times 12 is 24. If I subtract 4x to both sides, I get x. If I subtract 18 to both sides, I get 6. That's one part of my answer. Find the value of x. Now let's find the measure of angle ABC by substituting 6 into 5x plus 18. That's 5 times 6 plus 18, which is 30 plus 18, which is 48 degrees. That's the measure of angle ABC. Okay, that's the end of review worksheet number 1. Now, all these might hit more questions that are like that, but that's the end of that review worksheet. Flip to review worksheet number 2. Here we go. For numbers 1 through 3, tell whether the lengths can have the side lengths to form a triangle. Basic premise of this for a triangle is that the sum of the two shorter side lengths must exceed the longest side length. If I have side lengths A and B shorter than some side length C, A plus B must still be greater than C. If it's equal to C or if it's less than C, it's just not enough length to connect themselves up and make a triangle. Now, these are going to be pretty obvious answers here and there, but I will show you the test. We're going to compare the lengths 3, 8, and 10. 3 plus 8 must be greater than 10. Is that so? 11 is greater than 10, so yes. That's true. Therefore, these three lengths can make a triangle. It's possible to form them up to make a triangle. 11 plus 21, the two shorter sides there, we have to test and see if that's greater than 32. Well, 11 plus 21 is 32. 32 is not greater than 32. No, they can't connect up to actually make the triangle. If they do connect up, they're the same length as the third side. Therefore, they can't bow up to make the triangle. They just make another line right next to it, another segment, so it's not enough. 8.1 plus 7.8 here. We have to see if that's greater than 15.6, the largest side. That's 15.9 compared to 15.6. That is indeed greater. Yes, that can make a triangle there as well. Now, I don't think these review sheets does have the set of questions. I have them on my IM2 one somewhere. I don't know specifically where, but where you're trying to find the range of the third possible values. They exist somewhere there. You definitely want to use this inequality bit for that. All right, some more of these questions here. Write an equation of the line passing through -4, 5 and is perpendicular to the line with this equation here. So this is y equals mx plus b form. I don't see a y-intercept. That must mean it's 0, but that doesn't matter. We're going to find a new one for this. But what we do have to do is come up with the opposite reciprocal slope. If the original slope here was -4/5, the perpendicular slope is going to be positive 5/4. So our equation is going to be some y equals 5/4 x plus b. Let's find out what that b is by substituting 5 for y and -4 for x. 5/4 times -4 plus b. -4 times 4 is -1. So that's 5 equals -5 plus b. If you add 5 to both sides, you end up getting b equals 10. So this equation will be y equals 5/4 x plus 10 right there. Okay, write an equation of the line passing through -5, 2 and is parallel to the line y equals -3. Well, I'll tell you right now the answer is going to be y equals 2. Here's the idea. Y equals -3 is in slope-intercept form. It's y equals 0x, minus 3. 0x minus 3. The slope of this line is 0, so the slope of the line parallel will be 0. So we need some equation that's y equals 0x plus b. Let's substitute 2 for y and -5 for x. 0 times -5 is 2, therefore b equals 2. So our equation will be y equals 0x plus 2, which is also y equals 2. If you think of this I didn't do all of that in my head. What I did was I knew that y equals -3 is a horizontal line. How can you have a horizontal line such as y equals -3 right here? That doesn't look very horizontal. Here's that negative 3. Make it parallel up here with y equals 2. And how's it supposed to pass through negative 5 comma 2 without just being the y equals 2 equation? I mean, that's all it was going to be. It's a parallel line crossing at y equals 2. Excuse me, crossing at negative 5, 2. That's going to be y equals 2. Okay, number 6. And I know there are easier problems than this to work out later, but find the perimeter of the triangle with vertices 0, 1, 5, 4, and 2, 6, round to the nearest 10th. What you want to do here is you need to find the distances between these values. And I say easier for other ones because you actually have a graph for them. I prefer to not use distance formula as often as I can avoid, but maybe this time I will use distance formula and other times I won't just because there's no graph here. But I might support it with some drawings in a bit. Okay, the distance formula itself is d equals the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And I want to state right now, this is a variation of the Pythagorean theorem. What is this x2, x1, y2, y1 stuff? You got to choose 2 points, any 2 points like these two right here. Coin them some sort of x1, y1, x2, y2 like this. Substitute those values in. The x2 minus x1 is finding the distance between our x values. So let's find some distances here. Let's do this one here. Some first distance between these 2 points is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. The distance between 0 and 5 is 5 minus 0. Square that, because Pythagorean theorem stuff, I'll tell you about that later. Hold on a second. There's very little room on this problem. Is 5. 5 squared is 25. 4 minus 1 is 3. That's the distance between 1 and 4. 3 squared is 9. And that gives me the square root of 34. Now, I'll leave it exact for now. We'll go ahead and round at the very end, but that's probably somewhere kind of close to 6. The square root of 36 is 6, so the square root of a little less than 36 is going to be a little less than 6. Maybe 5.8 or something. I don't really know. So that's one of my distances there. Let's find the other 2, right? This is a triangle here, and that was one of the sets of points that it goes through. What's another set of points that it goes through? Well, it can go through, say, let's get another color. Go through, say, 5, 4, and 2, 6. So we'll have a new x1, y1, x2, y2. So let's check that out. The square root of, let's do 5 minus 2 quantity squared plus 4 minus 6 quantity squared. 5 minus 2 is 3. 3 squared is 9. 4 minus 6 is negative 2, but negative 2 squared is still a positive 4. That gives us the square root of 13 right there. And that's another distance, somewhere between 3 and 4, right? Maybe a little more than 3.5. But we'll add them in a bit. Now let's do the last set of points here, which is 0, 1 with 2, 6, right? Those also connect to each other, 0, 1, and 2, 6. Let's call it D3. That's the square root of, let's do 2 minus 0 squared, x2 minus x1 squared, plus y2 minus y1 squared, 6 minus 1 squared. Square root of 2 squared is 4, and 5 squared is 25, which is square root of 29. Very little room here. Now, perimeter is the sum of all these distances right here. Root 29 plus root 34 plus root 13. Perimeter is root 29 plus root 34 plus root 13. Now, you don't add 29, 34, and 13. We're actually going to take those square roots. So I'm going to do that with you right now. Root 29 plus root 34 plus root 13. 14.82, around 14.8. 14.8 units, whatever the units are supposed to be there. Okay. So that's the distance around all of those. Now, again, there was no drawing with this one. I'll give you a rough version of that drawing and then support how I'm going to be doing these later if I do have graphs, or probably just use the graphs, because that seems like a lot of work to mess up at some point later. Later, I'm going to talk about Pythagorean theorem with you guys, but you were finding the distance, you were finding the perimeter around this triangle at 0, 1, this is going to be a rough sketch, around 0, 1, 5, 4, and 2, 6, like this. So we found 3 different distances here. We found this distance here to be root 29, this distance here to be root 13, and this distance here to be root 34, like that, and we added those 3 up. And we'll talk about how we find those actual distances using what I just did for distance formula. but in a Pythagorean theorem way with graphs, or just, just like that, even on a rough sketch. Okay, what is the slope of the line that's parallel to the line passing through the points 5, -3, and -1, 4? So for y equals mx plus b form, we need both m and b. By the way, I don't need to do y equals mx plus b form. I can also do y minus y1 equals m times x minus x1. I'll give you 3 different answers, even in the skinny version right here. To do this, we do need slope. Now, slope is, in the same way as I just showed before, there's a slope formula. It's kind of like distance formula. y2 minus y1 over x2 minus x1. You got to find the distance between your y's and x's. You don't square anything, but you do divide them. So if I have some x1, y1 right here and x2, y2, I can say my slope is y2 minus y1 over x2 minus x1, which is 7 over -6, so -7/6. So here's the slope of my line. Now, one version or 2 different versions of your answer you can use is using point slope form right here. And you can use either of these points, this xy or this xy, for your answer. You can either, if I use this as my x and y, or x1, y1, I'll say y minus y1 minus -3 is +3 equals m times x minus x1. There's one version of the answer. Another version is this is my x1, this is my y1. So y minus y1 equals m times x minus x1 minus -1 is +1. Now there's a third version in y equals mx plus b form. Oh, they didn't ask for the equation. I'm sorry, they didn't ask for the equation. They just asked for slope. So I am going to stop there. I'm going to stop there. I was going to say a third option is y equals mx plus b form, but you would get a fraction y-intercept answer. But here is some point slope form stuff. I'll go and leave it at this. What is the slope of the line parallel to the line passing through these points? It is also -7/6, because the slope that we found is that, so this is also it. Number 8, what is the slope of the lines parallel to the line number 7? We just answered that. This probably meant to say perpendicular. Perpendicular. So I'll just go ahead and answer that. Perpendicular is +6/7. Yes, make sure you answer the question being asked and make sure the question is a proper one. All right, number 9. Oh, okay, this is the one I was referring to before with congruent triangles, which is not a congruency statement for triangles. Circle all that apply. Might be easier for us to first state the ones that are and then just ignore them after. Oh, it doesn't matter. All right, A, side-side angle. This is not one that I mentioned before because it is not one. Side-side angle, or as I sometimes write, angle side-side. Gee, that's a bad word. You can't say that. Well, then it also can't be a triangle congruence thing. Angle side-side is not a valid triangle congruent statement thing. I won't state why for now, other than to just let you know that there's more than one possible triangle you can make in a lot of those scenarios. A is something that does not work. Remember, not a congruency statement. I'm circling the wrong ones. Angle, angle, angle is also not one. That's a pretty easy descriptor as to why. I can make 2 equilateral triangles such as this and this. They can be completely equiangular, I should say. They're all 60-degree angles, but one is clearly bigger than the other. Those triangles aren't congruent. They are similar. That's the word. They are similar, but they are not congruent to each other. Angle, angle, angle does not work. Angle, side, angle works. Side, side, side works. Side, angle, side works. Angle, angle, side works. If you ever see them write side, angle, angle, it's the same thing. And HL also works. These are good. These are not. We will not use these. We cannot use these. We can definitely use these as long as we have them. Moving forward with congruent triangles. For numbers 10 through 12, state the theorem or postulate of why the triangles are congruent. Now, the nature of this drawing shows a shared side here. It's called the reflexive property, which shows that this segment in one triangle is congruent to this segment in another triangle. So I mark that, and then I show that this is a side, side, side case. Right there. These triangles have a side, angle, side, 2 congruents. Oh, hold on. Side, angle, side here, and this one is an angle, side, side case right there. I don't know whether these triangles are congruent or not, but this part is not marked to be congruent to this part, and that was the important part that we needed for side, angle, side. I don't know if these are congruent or not, but these are not guaranteed to be congruent. These are not necessarily congruent. There's not enough info to guarantee these are congruent. So you don't just look at one and say side, angle, side. You're trying to correspond parts. This corresponds with this, and this corresponds with this, but I don't know if they're congruent to each other. And this is an angle, side, side case, so we can't guarantee. Not enough info. This last one right here is a right triangle set, shared congruent sides right there, and then these two hypotenuses congruent. This is an HL case. Not just because they're right triangles, but in these right triangles, the hypotenuses are congruent, and there's one set of congruent legs. That is what HL stands for. So there. All right, state which triangles are congruent and why in these cases here. This time we actually have to also have a triangle congruent statement. So one more time, we have shared sides is the reflexive property here. And I have this triangle, angle, angle, side, congruent with this triangle, angle, angle, side. Let's correspond parts. Triangle FGI, boom, 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 congruent to HGI. Congruent to triangle HGI by angle, angle, side. That works out. Once again, the reflexive property here shows two congruent. You're going to see that a lot of shared sides. Side, angle, side right here. Let's call this RSU with TSU right here. Triangle RSU congruent to triangle TSU by side, angle, side right there. This last one, once again, shared side right here, reflexive property. But now be very careful. This is angle, side, angle. That's fine, angle, side, angle. But look at what corresponds. The K in this triangle corresponds with the M in this triangle. And then the M in this triangle corresponds with the K in this triangle. So be very careful how you name this. It's not like JKM and LKM. Instead, it would be some other version. Let's start with K. Let's say KJM, triangle KJM, congruent to. Notice that's the one arc marked to the none to the two. Let's go to the one to none to two. MLK. Martin Luther King, baby. MLK by angle, side, angle. Angle, side, angle right there. So you see the difference there. That's more of a rotation, whereas this one was more of like a reflection, if you will. And this one was kind of like a reflection. Okay, they were all congruent there. All right, 16 through 18. State which best describes each construction. Now, I didn't get to do construction with my group this year. I sure hope we get to next year. They're kind of fun. You would do this kind of construction to create two congruent angles. Congruent angles. I don't know if I want to explain what the construction part is. What you do is you use your compass, and from some, you would just have this ray right here. And from this, what you would do is you would draw, you would have one of your angles right here. You'd have some angle right here. And then over here, you would draw some ray. And then at some point here, you would make some arc with a compass here and draw the same arc with that compass here. Wherever this point intersects here, you can create a new arc that for sure goes through this angle and recreate the arc through there. And wherever it hits through is where you draw your ray through. That's congruent angles. If you haven't seen that before, you probably have no idea what I'm talking about. If you have, then it's probably okay. This one right here, this constructs what's called a perpendicular bisector. Now, a perpendicular bisector itself is if these are two endpoints here and here, this line hits through the midpoint of these two, it bisects it, and it intersects perpendicularly. Now, how do you do it? You take your compass at one endpoint right here and make it a fixed width past halfway. As past halfway as you can kind of get, draw its arc. Keep the same arc width or length of your compass on this side and go and draw another arc on the other side. Where these 2 points intersect, you use a straight edge to draw straight through there, and that straight through there should go perpendicularly through, and it should bisect it if you didn't change the width of your compass from one to the other. It's a perpendicular bisector. This last one here is an angle bisector. Angle bisector. What this one does here, an angle bisector divides an angle into two congruent parts. What you do is you start with this angle right here. You start with some angle. And then from the vertex, you create an arc with a compass width. Doesn't matter what the width is. You just make it an appreciable distance here. And then from this point here and this point here, you fix your width at some other arc that'll definitely go past some halfway point of where your bisector is. So from here, you draw an arc, and then you go over here and you draw another arc. Where they intersect right here is where you draw your ray through. And that ray ends up becoming an angle bisector, divides into two congruent parts right there. They're kind of fun. I miss doing those. All right, number 19, find the perimeter of the figure below. Here's an example of me I'm going to use Pythagorean theorem this time instead of distance formula. I say that in that distance formula is Pythagorean theorem, but I'm not going to plug them into an equation like that so much as I'm going to plug them into just this equation right here. If you have some right triangle with leg lengths A and B, and hypotenuse C, the relationship is a squared plus b squared equals c squared. This means that if you want to find any diagonal length for something, you can use the horizontal and vertical lengths to come up with them. And that's important for these lengths here because I can count this distance here and this distance here to find out, in this right triangle, what this third length is going to be for all of them. And I can do it for all these here. So this is the length MN right here. And I can count this distance. This is 1, 2, 3. And this is 1, 2, 3, 4, 5, 6. This is my x1 minus x2. And this was my y1 minus y2. And I'm just going to square those the same way I would do here. So 3 squared plus 6 squared equals mn squared. 3 squared is 9. 6 squared is 36. So mn squared is 45. So mn is the square root of 45. Now that's exact. I can't take its square root exactly there. I can't. It's not a perfect square. And I'm not going to, there's a simplifying radical version called 3 root 5. I ain't doing that with my kiddos right now. And my thing, I'm going to round these to the nearest tenth anyway. So I'm going to leave it as the square root of 45 for now. My kiddos might approximate it beforehand. I'm just going to leave it like that. Let's go ahead and find NJ. Let's do another right triangle here. This distance is 1, 2, 3, 4. This distance is 1, 2. After a couple of these, I'm going to do it pretty short-handed. I might not even show work on them. 2 squared plus 4 squared equals NJ squared. 2 squared is 4. 4 squared is 16. So NJ squared is 20. So NJ is the square root of 20. Again, not a perfect square there. So I have root 20, root 45. I still have 3 more to do. Now this one's pretty nice. Look at this ML. Check this out. These distances are 1, 2, 3, 4, and 1, 2. Well, we already saw one that had distances of 4 and 2. Do you think its length over here is going to change with these being the same? It's not. That makes ML the same length as NJ. This is also the square root of 20. I've already saved myself some time not needing to do Pythagorean theorem there just by seeing those distances. Now this one right here, KL, this distance is 3 and this distance is 4. I can tell you right now this answer is 5. If you know Pythagorean triples, you might know it's a 3, 4, 5 triangle. But let's try it. 3 squared is 9. 4 squared is 16. That equals KL squared, which is 25. The square root of 25 is 5. That's me writing a little more shorthand. That's 5. And the last one, let's try and do this completely mentally. Let's see how good we're able to work that out. KJ. This is, let's just count this out. 1 and 3. 1 squared is 1. 3 squared is 9. 1 plus 9 is 10. KJ is the square root of 10. So we have all 5 distances here. Now we need the perimeter based off of that. We have them written. So the perimeter is root 10 plus root 20 plus root 45 plus root 20 plus 5. The square root of 10, like, remember, it's not, you don't actually add the 10, 20, 45. You take their square roots and such, and then you come up with those. So root 10, that's a little more than 3, plus root 20, that's somewhere between 4 and 5, about 4.5, plus root 45, that's a little under 7, plus root 20, another 4.5-ish, plus 5. If I were to guess, let's see, root 10 is a little more than 3, the root 20 is about 4.5 each, so what is it? So that's like 9-ish, plus a little more than 3 is about 12-ish, plus 45, it's a little 6-ish, so let's say 12, 6, about 19, plus 5. It's going to be around 24. I'm going to say it's going to be a little under 24, I guess, 23.8, I don't know, 23.8. I promise you I haven't seen this answer before. I was just saying it's going to be a little under in some sort of way. I promise you haven't seen that. And even if you're like, yeah, sure, you have, well then good, I memorized it. Yay me. But I'm just coming up with what I think it's going to be close to. There's the work. All right, find the area of the figure in number 19. Ooh, that's a little freaky. Okay, so I'm going to erase my work up here to kind of get another set of work going on here. Now, area comes from doing some form of, I don't know, the shapes that you have. There are a lot of different shapes I can come up with on this. I'm just going to go and break it up in some composite figures. I got a lot of triangles here. That triangle, ooh, that triangle's not a good one. Hold on a second. Okay, I don't know about that triangle. Let's break that up in a different way. Let's break that up maybe right here. And then this triangle right here. And then this rectangle right here. This rectangle right, this triangle right here. Okay, there are a lot of different things. Oh, and a trapezoid. We can work out a trapezoid too. I don't know if you know trapezoid formula, so I'll just go ahead and only do triangles with you guys. So you got to find the areas of all of these individual triangles and rectangles right here. Let's start off. I gotta sneeze. Excuse me. And I heard my phone go off here. Okay, let's start off with let's just write out some lengths. I have 3. I think 5. This distance here is 2. I'm gonna need that. That distance here is 2. This is a little 2 here and a 2 and a 1. And boy, I'm gonna run out of what I'm gonna work with. All right, let's just do one part at a time. That's fine. All right, in this rectangle, I got a 3 by 5 rectangle. Area is base times height. 3 times 5 is 15. I have a 2 by 2 square here. That 2 times 2 is 4. Now, area of a triangle is 1/2 base times height. If the base is a side length here, the height is perpendicular to it. That's why I was writing things like this was 2, because I got to do 1/2 of this. 1, 2, 3, 4, 5 times 2. So 5 times 2 is 10. Half of that is 5. 2 times 1 is 2. Half of that is 1. 4 times 3 is 12. Half of that is 6. 3 times 1 is 3. Half of that is 1.5. So that one's a little different. And then 1, 2, 3, 4, 5 times 2. Half of 2, that's also 5. Like that right there. Okay. So we're going to add up all of those. Find the area there. So that is 5 plus 5 plus 15 plus 4 plus 1 plus 6 plus 1.5. All right. 10, 25, 29, 30, 36, 37 and a half square units. I should probably put units for this other one in some sort of way. All right. All right, give reasons for the proof below. Well, I don't have a diagram. I'm going to assume that they just have a diagram that looks like this. 1 and 2. I didn't do this problem with my kiddos. All right, 1 and 2 are a linear pair. That's given, you see? Angles 1 and 2 are supplementary by definition of a linear pair, because they are straight angles add to 180. Measure 1 plus measure 2 adds to 180, definition of supplementary angles. I don't really know if I did that correct. I believe that might be. But a linear pair is by definition is supplementary. And then if they add to 180, definition of supplementary angles. I don't know if I did that right or not. I didn't do this problem with my kiddos. But there's a 2-column proof without a drawing. Now it has one. Okay, great. Sorry about that. Kind of weird problem. All right, find the length of x in all these. Now this goes back to what I just talked about, Pythagorean theorem here. This is your a squared plus b squared equals c squared. We just did it in action before. I might show less work over time as we do a few of these. I don't know. 9 and 12, I can tell you right now, this is going to be 15. 9 squared plus 12 squared equals x squared here. That's 81 plus 144. X squared is 225. And take the square root of both sides. X equals 15 right there. Something called a Pythagorean triple. Like the same reason I knew that other length was going to be 5. This one, I don't know. Off the top of my head, it's not a Pythagorean triple. 3 squared plus 7 squared equals x squared. 9 plus 49 equals x squared. X squared equals 58, so x is the square root of 58. If you round that thing, it's around 7.6. Right there. All right, this length is going to be 8. Now, the difference here is this time x is not the hypotenuse. X squared plus 6 squared equals 10 squared. 10 is the hypotenuse. It's the one opposite the right angle. So x squared plus 36 equals 100. X squared equals 64. The square root of both sides there, you get x equals 8. Okay, so you see what's going on. Let's see if we can now start to do these a little more mentally here. X squared plus 6 squared is 36 equals 20. I don't know, 24 squared. Is it 576? 24 squared, 576. Well, I might need some of that. X squared plus 36 equals 576. If I subtract that, you get x squared equals 540. So x is the square root of 540. Square root of 540. Which is around 23.2. It's exactly 540 though, so that's why I'm writing both of them. I want to make sure that you kind of have one and the other. Now I know this exact answer is the square root of 2. I just wrote a 5 and I said 2. Square root of 2, and I think you should know that as well because you're just doing 1 squared plus 1 squared. 1 squared plus 1 squared equals x squared. 1 plus 1 equals x squared. X squared equals 2, so x equals the square root of 2, which is around 1.4 something. Square root of 2, 1.414. So I'll just say 1.4. And lastly, is that a Pythagorean? No, it's not. Not that I know. Oh, wait, 512. No. No, maybe it's not. Let's work it out. X squared plus 24 squared equals 30 squared. Is it though? Oh, yeah, it is. Yeah, it is. Yeah, this would be 18. It just didn't look it because that's 18. Anyway. X squared plus 576 equals 900. That gives you x squared equals 424, which I believe is x equals... Oh, I'm sorry, 324, which is x equals 18. Okay, there's some Pythagorean theorem for you. Okay, we're going to do some segment addition postulate next on the next 6 problems at least here. We've got to solve for x in the first 2. Where what you have in blue is measuring the length of the entire bar, even though it doesn't look like it ends right at there, just pretend like it does. It's telling you that this whole length is 23. Now these segments are collinear, which means I can add all 3 lengths up and it equals the whole thing. So I can create an equation that says x minus 6 plus 9 plus 2x minus 19 equals 23. Combine like terms, x plus 2x is 3x, negative 6 plus 9 is 3, minus 19 is negative 16. Add 16 to both sides, and divide both sides by 3. You get x equals 13. So I'm going to go kind of fast on the algebra after that. The setup is all, right? So now we get to add these, 13, 6, and 2x minus 18, and we get 4x minus 29. 13 plus 6 is 19, minus 18 is 1. 2x plus 1 is 4x minus 29. Subtract 2x from both sides, add 29 to both sides, and divide both sides by 2. You get x equals 15. Okay, for numbers 9 through 12, find the length asked for in each. Now, I'm actually going to start with number 11. It's the easiest of the 3 here because these contain some overlap. This one does not. In order to find the length, you have to first solve for x. So the setup is going to be the same as the ones before. I can add up 3x minus 28 with 3x minus 30 with x, and I get 33. And 3x plus x is 7x. Negative 28 minus 30 is negative 58. If you add 58 to both sides, you get, I believe, 91, and divide by 7, you get 13, I think. X equals 13. Now, I'm not done yet. I got to find the length of DE. DE means I have to take 13, that x value, and substitute it, where you'll get 39 minus 28, which is, I'm sorry, that's a 28 right there. I know I'm cutting it off. What, 11? So DE is 11. Now we're going to do the same for others. We've got to solve for x, and it's going to be a little bit different here, just based on how it's written. You can see that you have some expressions set up a little differently this time, and sometimes you got to do a little more work to this. It depends on what you want to do and what you want to do to make it easier. There's more than one version. But let's play it this way, just so it makes sense. This length right here, notice that CE is x plus 26. And then you have BD is 27 plus x. So there's a little overlap. If I told you that this length was 10 and this length was, 16, you couldn't guarantee how much length was in between in the overlap. But you can compare, say, x plus 26 with 10. Let's say this length was 16 again. If this is 16 and this is 10, how long is that? Well, it's 6. You would do 16 minus 10. Now, I don't know that this is 16. I'm just saying, for example, that's what you could do. So if I want to get an expression for the length of CD here, I can. And I can use that by doing this length minus 10. CD is x plus 26 minus 10. That minus that, and then you'll get x plus 16. So I can express this as x plus 16 like that. It's kind of nice. So this is one version of what I can do. Why does this help me? Because now I have an expression I can use right here to compare these ones to get to solve for x. I can say this plus this equals that. And although they don't have a single length in and of themselves, it's not like it equals 40. I can still solve for x within that and then find the length of CE as requested later. So do 3x plus 47 plus x plus 16 equals 27 plus x. 3x plus x is 4x. 47 plus 16 is 63. 27 plus x. Subtract x. Subtract 63. I'm going to get a negative. Negative. I'm really bad at this math sometimes. 36. Divide by 3, you get x equals negative 12. And it's okay to get a negative x as long as the length stay positive. And it looks like no matter what I plug in for x, they probably all do still turn positive. So we got to find the length of CE. That's going to be x plus 16. Oh, excuse me. This is just x plus 26, right? CE is x plus 26. So negative 12 plus 26 is 14. I know this is messy work. It's a lot of all over the place. But if you followed what I did there, you'd be right on track. All right, BD. Let's move myself over now. And I haven't done these problems down here before, so my strategy might be different from yours. But we can do things the same way as before there. This one actually might be easier here. Let's write out an expression for just one of these and compare to the whole. So I have CD is 2. Let's take 2 away from, say, here, and then we'll just get BC's length. So if BD is 2x minus 4, if this is 2x minus 4, and then you take 2 away from it, then you'll just have BC. So BC, let's just do it right here. 2x minus 4, and then minus 2, which is 2x minus 6. So now I have an expression for BC as 2x minus 6. And now if I add 2x minus 6 with this right here, I can just do this one straight up, 2x minus 3. Then I'll get the whole thing 3x minus 1. I like that version. So 2x minus 6 plus 2x minus 3 equals 3x minus 1. Add 2x with 2x, get 4x. Minus 9 is 3x minus 1. Subtract 3x to both sides, add 9 to both sides, you get x equals 8. Now we got to find the length of BD. BD is 2x minus 4. So 2 times 8 minus 4, which is 16 minus 4, which is 12. All right, 12 right there. Okay, and last one as far as I'm concerned, EG. What's strategy? We got to find 14 plus x here. 12, we can get this part, and then this part plus that part can be the whole thing. Okay, so I'm going to take 12 and subtract 14 plus x to get this. And then I'm going to add this with this to get whole thing. I know that's a lot of just me strategizing there. So GH is 12, this part, minus the 14 plus x. Just keep in mind, you do got to do 12 minus quantity 14 plus x. The whole quantity. So 12 minus 14 minus x, which is negative 2 minus x. So GH is negative 2 minus x. Negative 2 minus x. If I add GH with x plus 23 there, I will get all of 26 plus x. So x plus 23 plus negative 2 minus x. That is just minus 2 minus x. And that equals x plus 23. Well, the x minus x cancels out. 23 3 minus 2 is 21. 21 is x plus 23. Subtract 23, get x is negative 2. Well, that's kind of weird because that means negative 2 minus negative 2 is 0. GH's length must be 0. Normally, I shouldn't accept something like that, but I guess that just means it's just not a part of what factors into everything, unless I did some math wrong. I'll double check on everything in a second. EG is x plus 23, so EG is negative 2 plus 23, which is 21. I don't know how I can double check on everything here, but 21 should be, if this part's 0, if that's 12, the whole thing is 12, that's 0. That's kind of hard to state how things really work there. I guess it works out. 14 plus x here would be 12. Yeah, this is 12 and that's 12. The whole thing's 24 here versus 21, but that's 0. I don't know if I did that right then. Negative 2 minus x plus 23. Sometimes the way that they write things don't work best either. I don't know. I'd have to look at this a little better and see if I did it right. 12 equals, or 12 minus 14 minus x, negative 2 minus x. I don't know. It looks fine to me. I don't know if I did it right or wrong, but that was my plan. If someone else gets a different answer, let me know in the comments section. Some of these problems can get a little weird. Depends on how they set them up. All right, here's some angle addition postulate. We did some before, so it should be pretty straightforward here. Actually, these are even easier. There's no real x to solve for. Find the measure of angle WDC. If measure of angle EDC, the whole thing is 145. And measure of angle EDW, just this guy is 61. So, I mean, I'll write this once. After this, we'll just go the easy way about it. But the angle addition postulate says the measure of angle WDC plus that 61 equals 145. So algebraically, you subtract 61 from both sides. Next time, I'll just say 145 minus 61. Measure angle WDC equals. Sometimes I really want my students to write something out algebraically. It equals 84 degrees. I really want you to write something out algebraically sometimes. And then just let the algebra take care of the rest so you're not overthinking what to do. Get the setup through the addition and then let the algebra take care of the rest. Especially if there are actual x's, combining like terms and stuff involved. But label the stuff. Find measure of angle IJA if AJK is 61 and IJK is 153. Well, same thing. We will subtract. So the measure of angle IJA is 153 minus 61, which is 92 degrees, I believe. See, this one's algebra here. It's worth adding them up instead of just saying, just subtract. Measure of angle HGF is 16x plus 4. Measure of angle, I think that's, you know what? This might have been an E right here. So HGF is the whole thing, 16x plus 4. Measure of angle EGF is 110, and HGE is 3x plus 11. Find x. So these two add up to equal the third thing. Again, this is where we can write that equation. 110 plus 3x plus 11 equals 16x plus 4. Combine like terms, you get 3x plus 121 equals 16x plus 4. Subtract 3x from both sides, 13x equals 117. Divide by 13, I do believe that is 9 for x, and you're done. This time, we have to find the measure of an angle at the end, so after we solve for x, we'll substitute. Angle GFN is 4x plus 10. NFE is 14x plus 3, and the entire thing, GFE, is 157. Find the measure of angle NFE, so we'll substitute for x there afterward. Let's start with the addition. 14x plus 3 plus 4x plus 10 equals 157. That's 18x plus 13 equals 157. Subtract 13, you get 18x equals 144. Divide both sides by 18, you get, I don't know if that's a clean number there. I don't think it is. 144 to 18. Oh, yeah, it is. It's 8. I added incorrectly to something. Anyway, it's 8. So we take the 8 and substitute it in to measure of angle NFE's expression. 14 times 8 plus 3 is 14 times 8, 112 plus 3 is 115, I think. $32.42. Yes, it does. Okay. All right. Use parallelogram to answer numbers 17 through 19. How about 17 through 20? Name two pairs of parallel sides. This angles part has to do with number 18. Name two pairs of parallel sides. So MH is parallel to AT. And then MA is parallel to HT. So parallel, parallel. Name two pairs of congruent angles. Opposite angles are congruent. Angle M is congruent to angle T. And then angle H is congruent to angle A. Whoops. Of course H is congruent to H. Come on now. Name two pairs of congruent sides. The opposite sides are also congruent to each other. So boom, 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 boom. So MH congruent to AT. And then MA congruent to HT. Name four pairs of supplementary angles, any consecutive ones. H with M with A with T, H with T. So angle H and angle M. Angle M and angle A. Angle A and angle T. Angle H and angle T. There we go. All right, in parallelogram ABCD to the right, the length of DX is 4 and AX is 6. Find each. Find the length of BX. Well, in a parallelogram, diagonals bisect each other. So if this is 4, so is this. That means BX is 4. XC again, if they bisect each other. If this is 6, so is this. So XC is 6. BD, that's the length of BX plus XD. 4 plus 4, or 4 times 2 is 8. And AC is 6 plus 6, or 6 times 2, which is 12. A lot of room for very little work. Actually, no work. All right, we have some transformations to do here. Graph the image of the image using the transformation give. Probably given. 3 units left, 1 unit down of BWI, it looks like it says. 3 units left, 1 unit down. Each point will go 3 units left, 1 unit down here. So that can be B prime. W, 3 units left, 1 unit down. This is a translation, by the way. W prime. I think that's an I. 3 units left, 1 unit down. I prime. And all of the parts, we connect the dots here because all those, the sides of all these points also go 3 unit left, 1 unit down to make that. There it is. Okay, across the y-axis. So the y-axis is your axis of symmetry. And this time I get to do a counting version of a reflection right here. W prime will be 1, 2 away from the axis of symmetry on this side like this. F prime will be 1, 2, 3, 4, 5 away. 1, 2, 3, 4, 5 over here. And maybe you just see how things correspond. F was 3 units to the left. Now it's 3 units to the right in the mirror. And this will go 5 away and 5 away right here, T prime, or a few down from F, about 4 down right there. And you see that reflection. And make sure you label the parts as well. Okay, across the line, y equals x. Now this is one where I think I can count this time, but I can also confirm that they go across the points like I stated before. So here's the line y equals x. It's that diagonal line, like so. All the points will hit across going the other direction. So like K and K prime are on the same spot. They're right on the line right there. But anything else I can count, say like this. I don't know what letter that is. What are these? K, E, S, and I'm going to pretend like that's an I again. So I can count 1, 2 across this way, and 1, 2 on this side is this other guy, I prime. E is 1, 2, 3 away. Oh, let me move that I prime then. E prime is 1, 2, 3 away from the mirror, so 1, 2, 3 away here. And S prime is 1, 2, 3 and a half away, so half, 1 and a half, 2 and a half, 3 and a half away over here, and we connect those dots. Now, maybe you prefer using the rule, but you'd need to actually have the rule itself for it. So you'd probably label out your parts. K was at 1, 1. You swap. Remember, you go from some point x, y, some other point y, x. So K prime is also at 1, 1. The x, y swap, you're still there. S was at, what, 1, 2, 3, I think negative 3, 4. So S prime is at 4, negative 3. Is it? 1, 2, 3, 4. 1, 2, 3. Yes. E was at negative 5, 1. So E prime is at 1, negative 5. 1, 1, 2, 3, 4, 5. And then I was at negative 4, 0. And now I prime is at 0, negative 4. 1, 2, 3, 4. Yes, it is. So those are the parts right there. Hopefully you can probably use a straight edge to draw those things, and then you're good. Across the x-axis, by the way, I don't think these have any rotations in this packet either. I don't seem to remember seeing any, so sorry for that. But across the x-axis here, here's the x-axis, and we reflect on the other side. Now the rules for these are, if you notice across the y-axis, before I do the x-axis, across the y-axis, the y's stayed the same, the x's just changed signs. Went from negative 5 to 5, and from negative 2 to 2. Here, the x's will stay the same, and the y's will change. So if that's another I again, then this is I prime. It's 1 away, 1 away. B is 1, 2, 3, 4 away. B prime is 1, 2, 3, 4 away. And W is 1, 2 away, and W prime is 1, 2 away. So there's a little overlap in this drawing, and it's okay that it happens. Just you still see the reflection, hopefully. And there it is. All right. But yeah, the y's changed sign there. The x's stayed the same. Okay, review worksheet number 4. We should be more than halfway done for sure, especially as we see some things that we've already seen. You know, we might run into some things we've already seen before. We're over 2 hours in, though. Describe the mapping of triangle EFG to triangle PQR. Well, at least they corresponded parts. EFG and PQR, they correspond there. But the mapping is asking what kind of transformation around where. If you see these things, they seem to be right across 2, 1 and negative 2, 1, 6, 3 and negative 6, 3, 2, 4 and negative 2, 4. They seem to be reflecting across the y-axis, or reflect across x equals 0. You can put that. Or you can put the rule. It's going from xy to some negative xy. The x's change sign, the y's stay the same. All right, describe why angle ABD is congruent to angle CDB. ABD is congruent to angle CDB, and why angle ADB is congruent to angle CBD. Well, this has to do with alternate interior angles, and it might be more, looking at the problems after this, it might be more important to look at those afterward. But if you look at the first set here, this is all about two parallel lines being cut by a transversal. I have this parallel line with this, it's marked up already, the parallel. Two parallel lines cut by a transversal. And if you notice here in blue, just ignore the green, ignore the black, just look at blue only. Two parallel lines cut by a transversal here. I have alternate interior, angles here and here. They're congruent when you have alternate interior angles. Excuse me, alternate interior angles are congruent when lines are parallel. Same thing for this one. This is two parallel lines right here. They're marked, cut by a transversal, and the ones in green. Ignore the blue, ignore the black, look at the green. Those are alternate interior angles there as well. When parallel lines are cut by a transversal, alternate interior angles are congruent. That's how you can prove those triangles are congruent with the reflexive property in between. So what we're doing after this here is we're looking at these lines here cut by this transversal, and we are naming the kind of angles that they are with one another. Vertical angles, linear pair, corresponding angles, things like that. Let's start with angles 1 and 2 right there. That is a straight up linear pair. We've seen those before already. Linear pair. Angles 1 and 3 is a vertical angle pair there. I'll just call them vertical angles. I'll probably abbreviate most of the rest of these. 1 and 5, these are angles that kind of face the same direction there, same side of the transversal, kind of that up and left thing. Example like 1 and 5 or 2 and 6, those are known as corresponding angles. Corresponding angles. 1 and 7 on the outsides here, opposite sides of the transversal, those are known as alternate exterior angles. I will abbreviate that as I say it out loud. Alternate exterior angles. 4 and 3, that's another linear pair right there for you. Linear pair. 4 and 8, another set of corresponding angles. Did they mean to do this? Corresponding angles once again. I was hoping to get some more, alternate interior, same side interior. 4 and 5 are same side interior right there. Same side interior angles. And 8 and 6 is another vertical angle pair right there. Not my favorite thing to look at. Where are my same side exteriors and alternate interiors? Come on. I gotta see all the sets there. Regardless, that's what we have. All right, use the same figure and the fact that line L is parallel to line M. Okay, now keep in mind, what I just wrote before was not under the assumption these lines were parallel. They were just two lines cut by a transversal. Those names still exist regardless of whether or not the lines are parallel. Linear pairs are always supplementary. Vertical angles are always congruent. But corresponding angles, alternate interior-exterior angles, are only congruent when the lines are parallel. Same side interior and same side exterior angles are only supplementary when the lines are parallel. So now we're going to play it under the assumption the lines are parallel, and now we're going to ask, with these angle relationships, the same ones, notice how 11 is like 3. Angles 1 and 2. Angles 1 and 3 here. Angles 1 and 5 here. Those are the same. Now they're asking, for that relationship when the lines are parallel, what's true? Are they congruent? Are they supplementary? Now, once again, linear pairs are supplementary. They would have been supplementary even if the lines weren't parallel. So I'm just going to say straight up, 11 and 15, supplementary, linear pairs. Vertical angles are congruent, whether or not the lines were parallel. Vertical angles would have been congruent anyway. 8 and 6, also congruent. Corresponding angles are congruent when lines are parallel. Look at that 1 and 5. As the lines kind of look parallel to begin with, those look pretty congruent to each other, right? 1 and 5. So corresponding angles are congruent. Alternate exterior angles, the 1 and 7, those are congruent as well. Notice the obtuse appearance of both of those. Alternates are congruent when lines are parallel. Same sides. Oh, here's another corresponding that's congruent. 4 and 8. 4 and 8. Same sides, like same side interior, are supplementary. We've mentioned that for parallelograms, right? One obtuse, one acute. Those are supplementary there. Same side interior angles are also same side exterior angles are also supplementary. Alternate interior angles are also congruent. So the congruent ones are the corresponding and the alternates. The supplementary are the same sides. Vertical angles are congruent. Linear pairs are supplementary. All right, for numbers 19 to 22, use the graph below, over here, that shows the value in dollars is worth after T years from when it was sold. Oh, a painting is worth. I did totally misreading that. Value in dollars a painting is worth after T years from when it's sold. So it's sold at time 0, I guess, for $1,800. 8 years later, this much money. 16 years later, this much money. So what was the painting worth when it was sold? $1,800. What was the painting's worth after 8 years? $4,000. You're just looking at the points. $4,148.20. After 24 years, skip the 16. $22,000. Go painting. $22,030. After 32 years, $50,770. All right, they don't want us to do anything else. That's it. Pretty easy. What is or are the intercepts of the graph below? This is the y-intercept at 5 or 0, 5. You just might say 5. This is the x-intercept. I guess we're just interpreting graphs on these. X-intercept at 2 or 2, 0. All right, for triangle ABC, list the angles in order from least to greatest. Like I said, opposite the largest angle is the longest side. Opposite the smallest angle is the shortest side. So opposite, so 6.1 is the smallest side. So opposite the smallest side is also the smallest angle here. So order from least to greatest, the measure of angle A is the smallest here. That's less than, what's the middle one? 6.2, opposite that is measure of angle B. Looks like we're going alphabetical. Which is less than measure of angle C, because that's 6.5. Longest side, opposite's the largest angle. Measure of angle C. Alphabetical, boom. Not always the case there. I forgot what I was going to say to this. Oh, unless you use what's called law of cosines, which is something you won't learn for a couple years into trigonometry stuff, you won't find out what the actual angle measures are. We're just comparing them. Which one's smallest, which one's largest. All right, what is the image of R using the translation right here? It should say the transformation because that negative x means it's some sort of reflection. So it should just be a transformation. So what we're going to do is apply an algebraic rule here to find R prime. R prime, here's the original x, y. The original x is -2, etc. The new x coordinate for this thing, we're going to take the opposite of the x, -2. And we're going to take the y, 8, and subtract 8, which means R prime is opposite of -2 is +2, and 8 minus 8 is 0. So here's where R prime is after that transformation is applied. Okay, numbers 26 to 28, find the slope of each line with the given equation. This is point slope form here. That is the slope in point slope form, so it's -5. I'm going to happily write -5/1 for you guys. This is standard form. You want to get it and say slope intercept form by getting y by itself. -2y equals -5x, subtract 5x. Divide by -2, y equals +5/2x. There's a +0 for the y-intercept, right? So, but this is mx plus b. The m is 5/2. That's the slope of that line. This one, x plus 4 equals 7. You can't get into y equals mx plus b form because there's no y to this thing right here, right? If I write it, this is x equals 3. That's a vertical line. That's a vertical line. That slope is undefined. Vertical line has an undefined slope there. Okay. Find the slope of the line perpendicular to the line with the given equation. So it's the same equations as above, right here it looks like, yep. And just find the opposite reciprocal slope. You flip, and that's good that I put 5/1 there. You flip those and you change the sign. +1/5. Perpendicular one here is -2/5. It's good that you did the work early on there, right? And then this one, this had an undefined slope because it was a vertical line. The perpendicular line is horizontal. Horizontal line has a slope of 0. Perpendicular line is horizontal and has a slope of 0. There you go. Okay, some more angle addition postulate here. Plenty of these involved, huh? Man, a lot of these. Measure of angle LMN is 135. That's the whole thing. And they're not tricking you any sort of different way. You're doing the same things as before. So I'm just going to go straight into it. -1 plus 45x here and 23x here. So you add -1 plus 45x with 23x to get 135, unless it's a fraction. 68x equals 136. Doesn't look it. Looks like x equals 2. Just had to find x. Here we have to find the measure of angle ABC after we solve for x. Let's see if we can kind of work this thing out. ABC is the whole thing. ABK is 42. KBC is 12x minus 4. So 12x minus 4 plus that 42 equals all of 17x plus 8. -4 plus 42 is 38. I like to keep my x's positive, so I'm going to subtract 12x from both sides and subtract 8 from both sides. And divide both sides by 5, you get x equals 6. We got to find measure of angle ABC. So we're going to substitute 6 into x. 17 times 6 is 102. Plus 8 is 110. 110 degrees for the whole thing. Yeah. All right. Find the slope of each line that goes through the following pairs of points. This time I'm not going to write the whole equation. Just find the slope. I'm not going to fall into that trap again. Yeah, I skipped all these problems with my kiddos. We did this last semester. Not that they remember how to do it necessarily. All right, so change in y over change in x. If I have some x1, y1, x2, y2, I'm going to do this each time for them, so I'm not going to rewrite that each time. Sometimes I might be able to do these out loud with you, but y2 minus y1, notice I'm subtracting the negative, over x2 minus x1. That gives me positive 6 over negative 9. I got to reduce that to negative 2/3. All right, let's do that again. y2 minus y1 over x2 minus x1. That's negative 2/5. Just kind of done there. And this one, y2 minus y1 over x2 minus x1. It's positive 7/5. All right, find the slope of the line perpendicular to, looks like the same point, so we just got to take the opposite reciprocals. So the slope of the perpendicular line is positive 3/2. Flip it, change the sign. This one, flip it, change the sign, positive 5/2. And flip it, change the sign, negative 5/7. Cool. All right, we have a rhombus. Hold on. Numbers 40 to 45. Use the rhombus, JKLM, and that stuff to find each. So in a rhombus, all sides are congruent, but it doesn't look like we're doing side things. We're only doing angle things. Opposite angles are congruent to each other. Consecutive angles are supplementary, same as a parallelogram. But also they're telling us it's a rhombus. Diagonals bisect each other, and they're perpendicular to each other. And they bisect their angles. So whatever this is, this also is. It's half of whatever something is. So measure of angle JML is 80 degrees. The entire thing is 80 degrees here. That means half of it is 40, 40, and 40. Now, all of these are right angles. Look, I'm going to fill out this stuff now, and then we'll see where we can get some answers with that later. These are 40, these are 40. Consecutive angles are not only supplementary, but in these right triangles here, this plus this should be 180. I'm sure we haven't run into those questions about triangle angles adding to 180 yet. I'm sure we got to get to those pretty soon. But that makes this 50 degrees and this 50 degrees. Again, they bisect each other. Or because these are 80 degrees, the whole thing here is 100 consecutive angles supplementary. So we have everything here, including this, like I said, 100 degrees. Let's just fill it out now. Measure of angle MLK. Okay, that's going to be the 100 here. That's 80, so that's 100. 100 degrees. JMK, that's 40. And JKM, also 40. Put N where the diagonals intersect. All right, there's a big N right there. Here's my N. JNM, that's a 90-degree angle. JNL, that's a straight angle. That's 180 degrees. And JKL is 80 degrees. That has nothing to do with the N, but that's okay. Okay, in triangle ADC, probably behind me here, in triangle ADC, identify all pairs of congruent corresponding parts. Now, in order to do that, you'd have to prove that the triangles are congruent themselves. They probably should say in triangles ABD and A and D, CBD, whatever. Let's prove these triangles are congruent here. Two angles congruent. If this is a right angle, so is that. It makes those congruent. This is congruent to itself. Reflexive properties, a shared side. So triangle ABD is congruent to triangle CBD by, it looks like, angle, side here, by angle, side. If the triangles are congruent, then all corresponding parts are congruent. Well, what corresponds? AB corresponds with CB. That means this is congruent to this. BD, oh, I already have that. AD is congruent to CD, boom, 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 and boom, boom, boom. And then this angle here is congruent to this angle right there. So identify them. I marked them. Let's just go ahead and call them out now. Angle A is congruent to angle C. Angle ABD is congruent to angle CBD. And angle ADB is congruent to angle CDB. The segments, we have segment AB, congruent to segment CB, and I like to write them in the corresponding order. Segment BD is congruent to itself, but really we're talking about in both triangles there. I don't know if this is how they want us to do it, but it makes most sense to. Oh, am I in your way of that? I'm sorry. I thought my picture was on the other side still. And then segment AD is congruent to segment CD. So those are the 6 parts, corresponding parts there. Okay, 2 more worksheets here. I think we have a few more triangle things to do now. What relationship is there with angles 1 2, and 3. They all add to 180 degrees here. Angle 1, measure of angle 1 plus, they're the ones inside the triangle, plus measure of angle 3 equals 180 degrees. What relationship is there with angles 1, 2, and 4? These are remote interior angles to that exterior angle. If you add 1, 2, and 2, that equals measure of angle 4. If you add 1 and 2, you get 4. I don't think that's true. But if you add the measures of angles 1 and 2, you do get measure of angle 4. We are going to be using that. What is angle 4 called besides obtuse? It's also called an exterior angle. Specifically, it's the remote exterior angle to angles 1 and 2. With respect to angle 4, what are the remote interior angles? So angle 1 and angle 2. So again, angle 1, 2 is remote to 4. 3 is adjacent to 4 right there. All right, use the figure below to answer what additional information is needed to prove triangle ABE is congruent to triangle CDE. Let's just make sure they have that written right. ABE, CDE, those would correspond. Okay, if you want an angle side angle case, notice we already have these angles congruent to each other in these sides. For angle side angle, you'd need the side to be in between the sets of congruent angles you have. That means we would need this angle congruent to this angle. We would need angle BEA congruent to angle BEA DEC. DEC, that'd have to be true. Now, I'll tell you what, those actually are congruent, right? Those are vertical angles, so I wouldn't need that information. I technically can deduce that. Other ones, when they talk about like angle side right here, like to show that this angle, it would have to be this angle congruent to this angle to have angle side, two angles congruent in the side outside of the angles. I have not, well actually, you know what? I have information to show that one too. These would be parallel lines. You don't know why, but these would be parallel lines, so those would be alternate interior. I guess you could deduce that as well. Anyway, you would need angle A congruent to angle C. Notice how I could only use one letter here. I was allowed to only use one letter here. In the previous one, I had to use 3 letters because of the ambiguity. By HL, for hypotenuse leg, notice these are both right triangles. Here are the legs that are congruent. You would need the hypotenuses to be congruent, these two segments right here. And I have no reason to guarantee that those should be congruent for any reason, so I would have to have these congruent. I'd have to deduce this. AE is congruent to CE. I'd have to have, I couldn't find that on my own, but that's what would give HL. And side angle side, side angle side, with side angle side, no reason to believe these are true either. But segment AB with CD, segment AB congruent with segment CD, that would have to be the case. All right, rectangle GEOM is not shown, but it has dimensions of 5 centimeters and 12 centimeters. Find GO plus EM. Now it's shown. 5 centimeters, 12 centimeters for G. Whoops, G, oh my goodness, GEOM. When they don't have it shown, I mean, you can draw it on your own, that's fine. What I want to show you is, in a rectangle or something larger like this, you have to circumnavigate your shape. GEOM, they have to go in that kind of order. I couldn't put GEMO, for example. The O can't go across the E, it has to be next to it. Anyway, 5 centimeters, 12 centimeters. Okay, I know where GO is now. GO is right here. EM is right here. They're diagonals. So here's the important aspect, right? These are rectangles. These are rectangles. That means these are right angles right here. And opposite sides are congruent. If this is 5, this is 5. So I can find the diagonal length right here because it's a right triangle. I can use Pythagorean theorem to find out what it is here. I can do 5 squared plus 12 squared equals GO squared, go squared. Now it's going to be 13. 25 plus 144 is GO squared. GO squared equals 169. If you take the square root of both sides, you get GO equals 13 centimeters. Now, EM is, diagonals are congruent in a rectangle, so EM is also 13 centimeters. GO plus EM is 26 centimeters. There's your answer. Ouch. Before I do WXYZ, This is kind of weird because, oh, hold on a second. Hold on. I don't know. This one says find the perimeter of GEOM, but this says for numbers 10 through 12, and clearly this is right below. I'm going to assume this is for WXYZ. Sorry about that. And WXYZ. If you want to know, the perimeter here would have been 34 centimeters, and the area would have been 60 square centimeters. But here, let's do this graph, and let's do the perimeter and area here like we did before. W is at 0, 4. X is at 5, negative 1. Y is at 1, negative 5. And Z is at negative 2, negative 2. Let's find the perimeter and the area. So we've done this before. Let's use Pythagorean theorem on these and find these out. I want to probably do most of this mentally. I'll do one of them together with you in case it's been a minute. Let's find out this length and use Pythagorean theorem on it. 3 squared plus 3 squared. 9 plus 9 is 18. So this is the square root of 18 here. This length here is 4 squared plus 4 squared. 16 plus 16 is 32. So this is the square root of 32. There are ways to simplify these radicals, which I'm not doing. We're going to do the decimal version. We'll just round to the nearest tenth. My back's been hurting. I'm having a lot of trouble. If you see me move my neck and stuff, I'm sorry. Oh, I got to do this for a second. Oh, man. Okay, let's see. I got to see a chiropractor again. Whew. 1, 2, 3, 4, 5, 6. 6 squared plus 2 squared. 36 plus 4 is 40. So this is the square root of 40. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 squared plus 5 squared. That's 25 plus 25, which is 50. So this is the square root of 50. So the perimeter is the square root of 18 plus the square root of 40 plus the square root of 50 plus the square root of 32. Again, I wonder if those can simplify to something. Oops, hold on a second. Square root of 18. Hold on, I want to guess what this is again. Plus square root of 50 plus square root of 32. Okay, let's see. I didn't press enter yet. Square root of 18 is a little more than 4. Square root of 40 is a little more than 6. Square root of 50 is a little more than 7. Square root of 32 is a little more than 5. Let's pretend like those are little halves that are adding, maybe a little less than that. So like 4.5, 6.5, so it's around 11. 7, actually that's a little closer to 7. Okay, let's just say 7. What did I say? 4.5, 6.5, 11 plus 7 is around 18. Plus around 5.5-ish, probably a little more than 5.5. 23.5. Let's press enter. 23.295. So I'll say 23.3. Boom. I probably overshot when I said. I actually thought it was going to be more. Well, that's a lot less than 4.5 actually. That should have been better. All right, find the area. Okay, let's erase our. Whoops. That's okay. I don't need the letters. Find the area. Got a bunch of triangles within here. Let's do... You know what you could also do? You could also do the area of this thing around and then subtract the triangle areas. I'm trying to decide which triangle areas would be better to do. Those ones. Let's do the alternative. Let's do what I'm saying right here. Let's take the area of this whole rectangle and then subtract the area of these triangles. Now, I had those lengths and I just lost them, but I can write them for you again. So this was 6 and 2. This was 5 and 5. This is probably how we should have done the other one before. The other one before wasn't a quadrilateral. This is 4 and 4. This is 3 and 3. So as whole lengths, 6 plus 3 is 9. 3 plus 4 or 2 plus 5 is 7. So the area is going to be 9 times 7. It's going to be the whole rectangle minus a bunch of these things we're going to add. We're going to have to do 1/2 of 6 times 2. Half of 12 is 6. Plus 1/2 of 5 times 5. 1/2 of 25 is 12.5. Plus half of 4 times 4. Half of 16 is 8. plus half of 3 times 3. Half of 9 is 4.5. So we're going to do 63 minus 6 plus 8 is 14. 12.5 plus 4.5 is 17. And that's 35. So that's 28. And I got to put square units for these. Units squared and then units for these. I think I got that right. I hope I didn't do any mismatch math. Oh, I'm sorry. 6 plus 8 is 14. Did I say 18? Hold on, I messed that up. See? 6 plus 8 is... If I said 18, I meant 14. 6 plus 8 is 14 plus 17, which is 31. So 63 minus 31. I didn't want to mess that up. So 32 square units there. Okay. Given line K is parallel to line L, prove angles 1 and 2 are supplementary. I don't know what they're going on about. Maybe we're missing some steps. Well, I know what to... I don't know what they want me to do here because they have these right here. K is parallel to L given angle 8 is congruent to angle 4 because alternate interior angle theorem, I guess. Prove 1 and 2 are supplementary. I don't know what they want me to do. Oh, they just say complete the beginning of the proof. They just say complete that part. I don't know what they want me to do there. I'm going to go and leave that blank. I don't like that version of that proof. I wouldn't want to prove a linear pair supplementary talking about alternate interior angles. That seems very backwards. Sorry about that. Hopefully what I did was fine. What can you conclude about vertical angles? They're congruent. They're congruent to each other. Angles of a linear pair, they're supplementary to each other. They add to 180. All right, the sum of the angles of a convex polygon is 3,240 degrees. How many sides does it have? Now, this is probably a more difficult problem than that of others we'd have to do. But here's what's going on. The interior angle sum of a polygon can be determined by taking 180 times the number of sides minus 2. This is the sum in degrees, the interior angle sum in degrees, and this is the number of sides. Normally, you'd have the number of sides and you try and figure out how many degrees there are. This time you have how many degrees there are, and you need to find how many sides. So 3,240 equals 180 times sum n minus 2 here. You can solve algebraically one of two different ways. Either you can distribute the 180 and then solve for n, or you can outright divide by 180 here. It better be a whole number, otherwise something's wrong with this polygon. It's not really working right. 3,240 divided by 180 is 18. So this is 18. That equals n minus 2. Add 2 to both sides. You get n equals 20. That's 20 sides. A 20-sided polygon has an interior angle sum of 3,240 degrees. It does not have to have all congruent angles and sides for it to have that interior angle sum. No matter what, they add to 3,240, just like no matter what, all the angles of a triangle add to 180 degrees, or a quadrilateral always adds to 360 degrees, and things like that, no matter what kind it is. Okay, now they say if it is a regular polygon, what is each angle measure? So we know there are 3,000, if I is the measure of one interior angle, then you take the interior angle sum and divide by the number of sides. If there are 3,240 degrees in the angles, I believe, and you divide by 20 sides? 20 sides, 3,240 divided by 20. You get 162 degrees per angle. That makes them, that's what would make them kind of work that way. Kind of like I said, a square or a rectangle, 360 degree interior angle sum divide by 4, because if they were all the same, you can just divide by 4 and they're each 90. So 162 degrees for this one in particular. It's very open. Like I don't have a 20-sided shape in my arsenal here, but I do have a 16-sided shape. So pretend like it was this one right here. See all the different angles right there? It's like all of these are 162 degrees, 162, 162, etc. They get closer and closer to 180 degrees the more sides that you add. If in number 17 the polygon's regular, what's the measure of each exterior angle? Okay, well let's go back to the one let's go back to the one that I just did with the pretend like this was my 20-sided shape. If this is an exterior angle here, these are my exterior angles. You extend the sides. So if this is 162 degrees, this is going to be a linear pair to it. This will be 180 minus 162, right? That's what we're going to be doing for that one. Whoops. Get rid of that. All right, so the exterior angle is going to be 180 minus your interior angle. So 180 minus 162, which is 18 degrees. Now, all the exterior angles should add up to 360 degrees, no matter what the thing is. So 18 times 20 is 360. That seems to work. All right, numbers 20 to 22. Find the midpoint of each segment with the following endpoints given. So in these problems right here, midpoint formula is based off averaging your x values and averaging your y values. You average values by adding them and dividing by 2. If there are 2 of them. Average, average. And it's an ordered pair. The final result's an ordered pair. We're trying to find out what's the midpoint between here and here. Well, it's this thing. It's right in between. We got to find an actual ordered pair. So the midpoint for this one is you take your x's, -3 plus 7, add them and divide them by 2. 2 plus -8, add them and divide by 2. -3 plus 7 is 4. 4 divided by 2 is 2. 2 minus 8 is -6. -6 divided by 2 is -3. The midpoint between those is 2, -3. And these are good to see on a graph as well. Even if you don't work them from the graph, it's good to make sense that you've got the answer in the right spot. And here, here you did. All right. Between 5, 0 and 0, 5, you average your x's here. You might be able to know this one already. This 5 plus this 0. 5 plus 0 divided by 2. And then this 0 plus this 5 divided by 2. So 5 divided by 2 for each of them. That's 2.5. 2.5, comma 2.5. As decimals. These are fractions. Not as fun. Not even for me. But let's do it. I got a little more space to work on this one. 3/4 plus -2 divided by 2. And then -5 plus 1/2 divided by 2. All right, -2 is -8 halves. So -8 fourths. 3/4 minus 8/4 is -5/4. I hate when I don't write correctly. -5/4 divided by 2. -5 plus 1/2. That's -10 halves plus 1/2 is -9 halves divided by 2. Now, dividing a fraction by 2 is multiplying the fraction by 1/2. We did that earlier with the exponential stuff. So that becomes -5/8 because 4 times 2. And then -9/4. The 2 times 2. Or as decimals, that would be -0.625. And -9/4 is -2.25. Like that. So either that answer, which I prefer, or that one, or a mixed number one I'm sure you could do. All right, 23 to 25. Find the slope of the segments with the following end. Oh, we did a bunch of these before. All right, find their slopes here. The same ones as before, only all the work we did not help for this one. Whoops, that's not a y. y2 minus y1 over x2 minus x1. That's -10 over, I think, +10 there, which is -1, or -1 over 1. This slope, I think, is -1. Y2 minus y1 over x2 minus x1, which is 5 over -5, which is also -1. Okay. And this one here, y2 minus y1 over x2 minus x1. 1/2 plus 10 halves is 11 halves. So 11 halves over -8/4 minus 3/4 is -11/4. So that's 11 halves times -4/11. The 11s cancel. -4 over 2 is -2. Whew. I'm not slowing down for you guys. Either you get it, or pause it, or you don't. Move on. Find the length of the segment with the following endpoints here. So this is more that distance formula / Pythagorean theorem kind of biz. Now, some of these you can do. Listen, I'm going to do these more in the Pythagorean theorem set because these numbers are pretty plain as day what you're doing. Let me draw one out and see if you can make sense of it. Here's 0, 0. Here's 4, 3, right? Instead of distance formula, I want to find out the distance between 0 and 4 and the distance between 0 and 3, so I can then find my distance here using Pythagorean theorem. It's what's the distance between 0 and 4 on x? That's 4. Distance between 0 and 3 on y? That's 3. 3 squared plus 4 squared equals d squared or x squared or c squared, whatever. Your distance, 9, this is going to be 5 again. D squared is 25, so square root d equals 5. But when I ask out loud on this one, because there are no negatives and no weird numbers, what's the distance between 0 and 3? Oh, I had these backwards, by the way. I'm sorry. It still gets the same answer. I'm sorry about that. 3, 4, so that's 3 and that's 4. Either way. What's the distance between 0 and 3? 3. What's the distance between 0 and 4? 4. Those distances between the points, right? 4 minus 0, 3 minus 0. That's what you're doing in those scenarios. So let's do the same thing here. Let's say it out loud. What's the distance between 1 and 6? That's 5. We're going to do 5 squared. What's the distance between 1 and 13? That's 12. We're going to do 12 squared. So there's your d squared in this case. We got an answer of 13 from this before. So I'm going to let you try that out and see if you can get it this time. D equals 13. Because I got that before with the exact same numbers in Pythagorean theorem. Actually, we might have used it to get 12. But see if you can get 13 on that one. All right, what's the distance between negative 6 and 0? Even if you say negative 6, distance should be positive for 1. But even if you say negative 6, we're still going to square that number. And that will still turn positive. But the distance between negative 6 and 0 is 6. The distance between negative 8 and 0 is 8. And we should be getting 10 for this one. So 36 plus 64. D squared is 100. So square root of both sides, D equals 10. Use your calculator for square roots if you'd like. Okay, so now we're going to find some missing angles with triangles adding to 180. It looks like some remote exterior angle stuff will happen here as well. And there are angles outside of the triangle as well with linear pairs. All right, we've got to find angles 1, 2, 3, and 4. Find the missing angles. So angle 1, 43 plus 74 plus the measure of angle 1 need to add to 180 right here. 43 plus 74 is 117. And if you subtract 117 from both sides, you get measure of angle 1 equals 63 degrees here. So that's 63. And you might want to write it, because this allows you to find things pretty easily after here. If this is 63, measure of angle 2 should be a vertical angle pair with it. It'll also be 63 degrees here. They're congruent. You can find 4 or 3 on your own accord. It's kind of up to you when you want to find them. I'm going to go ahead and find 4 first. 4 is a linear pair with 1 or with 2 right here, either or. So 63 plus, well, you can find 4 for a different reason. We could talk about remote exterior angles as well. Let me show you this. Either 63 plus 4, not 4, measure of angle 4. Measure of angle 4 equals 180. Subtract 63, measure of angle 4 equals 117. Well, where have we seen 117 before? Well, we saw it when we added 43 plus 74. Why does that give you 117? Because this is the exterior angle to these two remote interior angles. This plus this equals this. And guess what? Measure of angle 3 plus 79 should also equal 117. So you can do this one of two ways as well. You can either say measure of angle 3 plus 79 equals 117, and use that to solve for measure of angle 3. If you subtract 79 from both sides, you get 38. Or we could have done measure of angle 3 plus 63 plus 79 equals 180. 63 plus 79 is 142. And if you subtract 142 from both sides, you will also get measure of angle 3 is 38. So it's an either or thing. I don't think I'm going to do as many remote exterior angles here again, because we're going to run into them down here. So I'm just giving you the heads up that that's how we can work it. We can work it that way. All right, in fact, I'm going to show a lot less work this time, especially because the numbers look a lot better. Let's find measure of angle 2 first here. It's within this triangle. 70 plus 50 is 120. Plus this measure should give you 180. 120 plus what is 180? 60. So measure of angle 2 is 60 degrees. Measure of angle 1, therefore, is also 60 degrees. It is a vertical angle pair with it. 4 is a linear pair with it. That should be 120. And you could do 3 from those things here, but let's just add these to 180. 60 plus 65 is 125, plus 55 would be 180. 55. Measure of angle 3 is 55 degrees. So you can really do some work that way on your own as well, as long as you navigate through your triangles that way. And those numbers were a lot cleaner. It was a lot easier for me to do that. All right, 31 and 32, find the measure of the indicated angle. This is that remote exterior angle thing. We got to find measure of angle A. You add that with 20. Whoops. You add that with 20 and you get 56. Remember, these are remote to that angle there. There's another way. Look, you can do 180 minus 56 to get this angle. Add these up to 180. I get it. This does save a lot of time right here. There's a reason for this proof, and it circumvents that other aspect of it. So this is 36 degrees. Now these two, they want DCB, this angle right here. These two add up to become that third one. Again, saving the whole adding to 180 thing, you can work this out a lot faster that way. Because there's some that use algebraic expressions, which it probably really does help you to just work it out this way. And that's, I believe, 82 degrees. Yeah. All right, 82 degrees. Okay. Last review worksheet, last 2 pages. Let's see how we do. We are almost 3 hours in. Triangle MNP and triangle QNP have the following properties. MN is congruent to QN. PM is congruent to PQ. And NP is a common side. That will mean it's congruent to itself there. If MN equals 6 and MP is 15, QN is x plus 2, and QP is y minus 1, determine the values of x and y. Okay, I guess we didn't have to know NP. These triangles are congruent to each other, but we already have information to work this out anyway. So 6 and x plus 2 have to be the same. 6 equals x plus 2, therefore x equals 4. And then 15 and y minus 1 have to be the same. 15 equals y minus 1, so y equals 16. Oh, that's it. That's a lot of buildup for just that. I thought there was going to be this big, I don't know. If AD is 5y plus 7, okay, over here, 5y plus 7, and BC is 7y minus 3, what must be the value of y to prove triangle AED is congruent to triangle CEB by side, side, side? So basically what they're saying here is, you know, to make these two triangles congruent, to make these two triangles congruent here by side, 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 these two segments would have to be congruent to each other. For these segments to be congruent to each other, their measures must be equal. 5y plus 7 must equal 7y minus 3. We're trying to figure that out. So we solve. Subtract 5y from both sides. Divide both sides by 2. We get y equals 5. How are them Doyers doing? Oh, they're losing. Yay. All right. Y equals 5. This is May 30th, by the way. That would have to be the value of y. Okay. State which triangles are congruent and why. Note some triangles may not be congruent. Okay. Now you have to mark some things up. We've done a bunch of these before. Let's check it out. We got BC congruent to itself. That would leave us with an angle side side case, which is not one we can guarantee for congruence. Angle side side does not work. Even though we see parts that look like they would correspond, this is just not enough information here. Okay, so, whoops. Not enough info. I can't, look, they might be congruent. It's just not enough info. Angle side side. Ass. Not good enough. We have vertical angles right here, which said this would be congruent to this right here. We have an angle side, angle side case here, angle side. That's fine. Angle side's allowed. I can call this triangle, let's say ABD. I'm going to start the first one alphabetically, or as alphabetically as possible, and just correspond it. ABD with CBE. Triangle CBE. That would be angle angle side right there. Reflexive property says this part congruent there in this right triangle, angle, side, angle, with, like I said, I'll do it alphabetical, A, B, C on one of them. A, B, C, looks like D, B, C by angle, side, angle. All right, 3 more. These ones are already separated. We got an angle, angle, side case, the angle, angle, side. I can correspond that to that. That's fine, even though it's all congruent. Heck, this would be congruent to this. They're isosceles triangles. And yeah, we haven't really seen isosceles triangles here. I don't know if they show up. I know my IM2 ones, I have plenty of isosceles triangle things. But ABC is congruent to, is it DEF? Let's see, ABC with DFE. DFE. I suppose technically you could do DEF. You could find out that's congruent, and then you don't know what's necessary there. But I'm going to go with what's already marked. By angle, angle, side. All right, these are in between. It's an angle, side, angle case. That works out. Let's call the first one ABC. Sounds good. ABC is congruent. You can do whichever order as long as the other part corresponds. From the none marks to the double marks to the single marks. None, double, single. EFD. EFD by angle, side, angle. Whoa. Angle. And lastly, we haven't really seen a side, side, side. We have reflexive property, shows those are congruent there. This would be angle, side, side, but it's a right triangle here and here. Hypotenuse is congruent, legs congruent. So that's going to be an HL. Triangle ABC is congruent to triangle DBC by HL. All right, works out. All right, numbers 10 through 13. State the characteristics of each. Whew. No. Oh, I think they just mean just define them. I was going to say all the properties. No. Yeah, I'll do that because I think we did that for the square, right? State the characteristics of square. We just said all sides congruent, all angles congruent. So parallelogram, opposite sides parallel. I'm just going to say that. Hopefully that's enough and okay. A rhombus, all sides congruent. These are like their definitions. A rectangle, all sides or all angles congruent. Or right angles. I'm trying to right. I'll just put right angles. Right. A trapezoid. One pair of opposite sides parallel. I know we haven't really done any of these. I'm not really going to work on those. An isosceles trapezoid. One pair of opposite sides parallel. And then the one pair, the non-parallel sides are congruent. They're also known as the legs. The legs are congruent. There are other things true about, therefore, the isosceles trapezoid, but we're not talking about properties. A kite, I don't have enough room to type all this. 2 distinct pairs of consecutive, I'll just put cons sides congruent. So let me draw out the trapezoid in the kite for you. Or isosceles trapezoid in a kite. Do they have a kite shape on this thing? Don't look like it. So here's a trapezoid. This is an isosceles trapezoid. Here's a pair of parallel sides. Boom, boom. The other sides are not. In an isosceles trapezoid, these two are congruent to each other. Boom, boom. In a kite would kind of look like this here. Might not be perfect. But a kite is like this. These two consecutive sides are congruent. These two consecutive sides are congruent. But 2 distinct pairs of consecutive sides are congruent right there. So these are uniquely congruent compared to that and things like that. And they're consecutive. Okay. Oh, here's some isosceles things. Okay, for numbers 16 through 18, find the indicated length or angle. Now, an isosceles triangle has 2 congruent sides and their opposite angles are congruent, otherwise known as base angles. If I have congruent base angles here and here, that tells me that this side is congruent to this side. That means I can solve for x by setting 4x plus 7 equal to 6x minus 5. Subtract 4x, I get 2x, add 5, I get 12, divide by 2, I get x equals 6. Now we got to find the length of AB right here. I'm going to substitute 6 for x into there. AB is 4 times 6 plus 7. 24 plus 7 is 31. And doesn't say centimeters or anything. So there's AB. All right, measure of angle T. Now we have isosceles triangle marked by these two congruent sides here. That means their base angles are congruent, right here and here. If this is x, so is this. Now all three angles in a triangle add to 180 degrees. So if I add the x's with this, what's called a vertex angle, the 3x, I get 180. 1x plus 3x is 5x. 5x is 180. Divide by 5. You get x equals 36. The measure of angle T is 3 times that 36 there, which is 108, I believe. 108 degrees. Use the units there. Now this triangle is an equilateral triangle. All angles are congruent. That actually makes them all 60 degrees, just so you know. But that makes all sides equal to each other. Boom, boom, boom. Doesn't really matter. I need to set this equal to this. So I have 3/10 y plus 9 equal to 4/5 y minus 1. Now we all hate fractions, including myself. So I'm going to get rid of them as soon as possible. I'm not going to worry about common denominator. I just want to multiply by a value that will get rid of all my fractions. So I got to multiply both sides by a number that can divide by both 10 and 5. Well, 10 can divide by both 10 and 5. So if I multiply both sides by 10 here, I do 10 times 3/10, or 10 divided by 10. 1 times 3 is 3. So I get 3y plus 10 times 9 is 90. 10 divided by 5 is 2 times 4 is 8. Here I get 8y. 10 times -1 is -10. You go, that's hard. Well, it's better than fractions. I like this a lot more, huh? Subtract 3y from both sides. I get 5y. Add 10 to both sides. I get 100. Divide both sides by that. I get y equals 20. Now, did we have to find something specific? Nope, just solve for y. So we got y equals 20, and that's it. Okay, last side. And then we're all done. 19 to 21, find the indicated angle. These are your remote exterior angle things from before, that these two add to equal the third thing. So I can say 6x plus 1 plus 5x plus 17 equals 126. This plus this equals that. This plus this equals that. This plus this equals that. The two remote interior angles to the exterior. 6x plus 5x is 11x. 1 plus 17 is 18. Subtract 18 from both sides. Divide both sides by 11. That does not look like a clean number. 108 over 11. Let me make sure my numbers added up right. Boom, 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 boom. Yes, they did. What is 108 divided by 11? Not a clean number. 9.818. I'm just going to leave it like that. Oh, measure of angle H. Great. So now I got to substitute that in. Was that the right answer? Let me make sure. 6x plus 5x is 11x. 1 plus 17 is 18. Subtract, I get 108. Yes, it was. So now we just got to... I will use my calculator value. I currently have this one right here. I'm going to use this exact one. I'm not going to retype it. It's already there. But I'm going to substitute that in for my h here. I know there's a fraction version, but I'll round the decimal for degrees. Measure of angle h is 6 times 108 over 11 plus 1. Now my exact 108 or 11 is already here. Plus 1. I'm getting around 59.9 degrees there. I'm going to go ahead and just leave it at that. It's whatever. It's close enough. I hope not all of these are like that. All right. This plus this equals that here. So now I have 63 plus 3x plus 7 equals 5x plus 50. At least if this is a decimal, it'll be a 0.5. So 3x plus 70 equals 5x plus 50. This one should be clean. Subtract 3x, subtract 50, and divide both sides by 2. You get x equals 10. Measure of angle N looks like we're doing 3 times 10 plus 7, which is 37 degrees right there. And lastly, I have this right angle right here. I'm going to mark it as a 90. That's the value for it. When I add 90 with x plus 2, I get 3x minus 8. 90 plus what x plus 2. Sorry, I was looking at what we got to find later. We got to find PRQ later, so we got to do a little thing for that after. X plus 2 equals 3x minus 8. That's x plus 92 equals 3x minus 8. If I subtract x from both sides, I get 2x. If I add 8, I get 100. So here we'll get x equals 50. Now this one's interesting because we do have to find angle PRQ. It's this one right here. So you kind of have options right here. If you find 3x, if you find this one right here, you can subtract that from 180, or you can find this one and subtract it from 90. I don't know if you know, but if these three angles add to 180, and if 90 is one of your angles, then these two just add to 90. So let's try that one. Measure of angle PRQ. PRQ is 90 minus 52. 50 is x, plus 2 is 52. And that is 38 degrees. So there's your answer. Now, if you want to do the other one, what's 50 times 3 minus 8? That's 142. And 180 minus 142 is also 38 degrees there. Okay, how many problems do we have left here? Almost done. 8 more problems here. All right, 22 to 23, find the unknown angle measure. Let's try and find these x's, I guess, right here. Now, all of these are 90, and it's probably good to write them all as 90s. This is a 5-sided, 5-angle shape. That is a pentagon. What's true about a pentagon's interior angle sum when we add all these things up? Well, I mentioned before that the interior angle sum is 180 times the number of sides minus 2. So that's 180 times 3, which is 540 degrees. That means if you add up all 5 of these angles right here, the 2x's and the 390s, there are other ways I could have written that, that equals 540, such as this. 2x plus 270 equals 540. This looks like a home plate. So this will probably give you what the angle measures right here are for a home plate, which is cool. 2x equals 270, so x equals 135. Each of those angles are 135 degrees. I don't have to put the degree symbol because it's already there. Ha! All right, so x is 135. Now this shape looks fun. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a nonagon. It is a 9-sided shape. We got to find the interior angle sum of the 9-sided shape. 180 times 7, I should know that, 1260. So these all add to 1260 degrees. I got to do x plus all these, 125, and I'm going to use the calculator, 130, 172, 200, 140, 102, 98, and 135. You add all of those up, you get 1260. So 125. What's sad is when I start to do it all in my head, like when I'm typing it out, sometimes I do it in my head faster. So far I stopped doing it in my head because now I'm talking to a camera. Plus 135. So that's 1102. So x plus 1102 equals 1260. I hope I didn't type anything wrong. If you subtract 1102, I think that's 158. 158. 158 degrees for that one. There you go. So you get the interior angle sum of the 9-sided shape, and then you add all the angles to that interior angle sum, and then find your measure. Okay, last few. We have this, find the value of n in each right here. So we have these mid segments right here, and in a triangle, such as these ones here, you have what are called similar triangles, and I'm not going to get too deep into the idea, but the idea is, if this is half of this length and this is half of this length, then this is half of this length right here. 6n is half of 48. Yeah, I can take half of 48 and I get 24. 6n is 24, so n equals 4. Here, 11.3 is half of n plus 4.2. And look, if you don't want to use the 1/2, you can go the other way. If this length is half of this length, then this length is double this length. So if I multiply everything by 2, instead I could say 2 times 11.3 is n plus 4.2. And I probably prefer it for this one. So 22.6 equals n plus 4.2. Therefore, n equals 18.4. If I subtract 4.2 from both sides, yeah, it's 18.4. Okay, same stuff right here. N plus 12 is half of 6n. Half of 6n would be 3n. Oops. N plus 12 is 3n. So subtract n, 2n equals 12. I don't know why these are all n. Divide by 2, n equals 6. Why don't we just use x? And then lastly, 4n plus 9 is half of 14n. Half of 14n is fine. That's 7n. Subtract 4n. Get 3n equals 9. Divide, and you get n equals 3. Okay, 2 more problems, and then I am all done. We're going to finish in 3 hours, 15 minutes. Same thing as, about 3 hours, 15 minutes. Same thing as my IM2. All right, this is a trapezoid, and there's a mid-segment idea in trapezoid as well that says if you average these two lengths, it equals this one. So if I average 12 plus 6, if I average 12 and 6x, add them and divide them by 2, I get 4x. Now I can't combine these, so I should probably just double both, so multiply by 2, multiply by 2. It's probably the way I should write most of them anyway. So 12 plus 6x, although I could have divided these by 2, equals 8x. Subtract 6x, you get 2x equals 12. Divide by 2, you get x equals 6. Find the length of the mid-segment. Did they ask for that here? No, they said find the value of n. So x is 6. The mid-segment is 4 times 6, which is 24. That's the length of the actual mid-segment. And lastly, I got to average the y plus 3 and 3y minus 7. Y plus 3 plus 3y minus 7 over 2 equals y plus 6. That's a plus. I will combine like terms up here, but I'm also going to multiply by 2 at the same time. I think it's just worth doing that part. So y plus 3y is 4y, and 3 minus 7 is negative 4. 4y minus 4 equals, I'm going to distribute this. Oh, I could have divided those by 2. Shoot. 2y plus 12. Let me move my picture for the very end here as we're nearing its end. Subtract 2y from both sides. Add 4 to both sides. And divide both sides by 2, you get y equals 8. The mid-segment in y plus 6 is 8 plus 6, and that is 14. All right. Sorry if that was too... Rip headphone users. Sorry, that is 14. Wake up. You're done. Okay, guys. Any more pages? Clean. That is it. Okay, that ought to do it for this one here, and I feel well accomplished with a very hurt back. So, we just did 16 pages worth of stuff. I hope you had fun doing all these here. Listen, there might have been things that were missing here and there. I didn't see a lot of proofs here. A lot of things in the IM2 section, though. If you go down to the description section, not just this one, but also the IM2 one, you will find some stuff that might have been missing here that maybe you wish that you had or that you did. That'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. Go Pirates, no go Dodgers. Take care. I don't know when the next one is that I see you, but I will see you in that next one, whenever it is. Bye.